Okay, good morning to one and all the participants to the last day of this FDP. Today we have a great speaker, great scientist, Dr. S. Shanmugan sir. He is from KL University. Dr. Shanmugan sir is the world's top 2% scientist from last 5 years. His special area is mainly related with the solar desalination. He is working on a he is on a several editor board member for the different publishers. And sir is highly respected researcher in the field of renewable energy, solar desalination, then hydrogen production and all these things. Sir, it's my kind request now. You can share your screen.
Yes, sir. Yes, sir. Yes. Sir,
Yeah,
my
that
voice is
will be
audible,
fine.
sir?
Yes, sir. Yes, sir. Yes, sir. Yes, it is. Just
Yes.
press F5. Yeah.
Yes, sir.
Yes,
Thank you
that's
for
fine, sir.
giving me this opportunities. The Department of Mechanical Engineering in Army Institute of Technology, Pune and India. So this last 5 days, very enjoying for the hydrogen production. So today, I think last day. So this section also very fruitful, and you can improve the your growth of the technologies, and based on the science and engineering, what your technology you can improve based on the your skilling, based on the your material you can select and developing for the your growth of the life. So welcome estimated professors, researchers, industry experts, and students to the 1 week AICT at all online FTP Hydrogen 360 Unlocking the Potential of Sustainable Power. This very fruitful for the here our FTPs and developing for the faculty development and the students and very motivation of our research work. This work you can go for this program to aim provide the comprehensive insight to the green hydrogen productions, storage, safety, and the real world applications. Yes, this global energy you can system and transmission towards the cleaner and pathway hydrogen standard to crucial and pillar to form of the sustainable energy development that very suitable for the sustainable development. Through the expert, the lecture and demonstration and interact for the many section I saw. So very interact for the to participation to will be explored for the innovative technology and engineering approach for the shaping the future hydrogen production for the your ecosystems. That system we are harnessed to the host to the academic gathering and look forward to the meaningful and learning and collaboration and technical and advancements. These all are very motivation of this FTP. So this FTP is you can growth of the very hydrogen technologies to understandings the covering and the production and the storage, safety and application for your particular goal. This goal you can use it the program and inbuilt and construction go for the future ready to for the engineering and researchers capable of contributing to clean energy innovation and sustainable development. These all are the focus of the our FTP and 360-degree. So this based on today I can discuss here some little bit I research what I have done that based on it can improve for the here engineering innovation for the hydrogen production and the solar desalination towards the such sustainable features. These all are the very important. So those important for the today we'll discuss for our title. These studies you can improve the innovation and integrate for the hydrogen production based on the solar desalination system to support future development of the societies. This works maximum solar energy use the clean energy generation while simultaneously production for the potable water and hydrogen material based on the your advanced nano material you can use it and enhanced thermal managements. These all are hybrid systems designs and integrated to improve the electricities and reliability and you can growth of the, your solar energy level. This level you can integrate and you can develop for the approach for the address global what is now global needed. That's you can improve the global challenge of the fresh water and the security and you can go for the clean energy demand. This focus of the combining, you can go to the solar energy driving that you can use it the involving for the electrolyzers. So this all you can why you can use it here. If you want, you can go for the more high performance desalination mechanism. That mechanism you can use it the your single slope or double slope or wick type. Any system you can use it to some achievement and low emission and high resource utilizations you can improve the your systems. This important of the highlight of the energy level, we can use it the potential of combination hydrogen and water production technology for the sustainable eco-friendly featured energy solutions. These all are the aim of the our engineering innovation for the hydrogen production and the solar desalination towards sustainable future. This is our aim. So here I given the three pictures. Some here new material, how internal molecule vibration you can get it naturally. This based on the suitable material to some you can activated carbon you can add it. Based on the activated carbon you can use it here waste material from argo material. That material suitable to after that how much you can binding you can get it the layer by layer. That's you can go for the composite materials. That composite material combined after then you can get it the which novel material you can prepare. That material based on you can go for the achievement. That's the SDG goal. Already you know. So as for the mechanical engineering, you know, based on the SDG goal, 17 is available. That 17, which one is you can achieve after then based on your proposal, based on your paper writing. That way, all you can do the your system that level only any one or two you can achieve. That's your credit you can get the very more popular for your research level. So this is a very important here. So my name is Dr. Ashan Maham. So I am working the current I am working deputy HOD of the IRD department. That IRD means you can know that's integrate research and discoveries based on the motherboard background of the physics background. So this is I am working in KL universities. That's called you can see the here Konar Lakshmi Education Foundation in the Andhra states. This location is Vijayawada campus. So this campus you can see the here. So totally 200 acres our universities occupied. This based on you can see the here our building working construction and here overall India. So here location there the Vijayawada. So this based on our laboratory and here central libraries is same times 4,000 students is sitting and inside the here all available facilities for the library and here all you can go for the here important to you. So today we are telling here all hydrogens. What is the important and why hydrogen is very important to you here nowadays for the society levels. So that's you understand. So this process, you know, that's the only gas. Already, you know, hydrogen means already gas form it only. So this gas, you can use it the which energy you can utilize. That's here you can use it the several energy sources available. But your research based on which one is you can use it, that level only you can follow. That's based on you can conducting and you can improve for the clean energy fuels. That based on the only adapt only solar energy only. So that's a especially you can use it the here when product and you can improve for the using renewable energy source. This all are you can use it the some method is available. Already you know method of the hydrogen production. Only here four types is available. Only water electrolyzer and SMR. After then you can use it the biomass gasification and another one is photocatalytics or you can telling the solar hydrogens. Among this, I can focus on here solar hydrogen only. So here fourth one is we are focused. This all are you can water electrolytes already you know that's a splitting water. Already you know that's a hydrogen and oxygens was electricity only they will form it. They when they powered by the solar, wind or other renewable energy sources based on the hydrogen, green hydrogen they will form it. Okay. So these all are the very important. This based on you can see the here SMR means already they're producing the hydrogen natural gas only. Okay, so that common method you can use it the some releases for the carbon dioxide. So that's a gray color they will form it. After then you can biogases gas clarification. That's a converting and agriculture or you can know organic waste material based on they will develop. That's a hydrogen rich gases. So yesterday, I think IIT professor, these all are full explained. So today I can go for the photocatalytics or you can see used here solar hydrogen production. That's a very using the sunlight and the catalytics and the split water directly. So these all are the very important. So you can use it the very important the point. You can use it the here clean energy carrier, high efficiency, zero emission at point of use. This point, which point you can use it, that based on the your thing, and you can use it for the very useful for the fuel cells, industry, power generations, and transportation. These all are the very important our goal. So these all are the important the hydrogen productions. Okay. So next come to the our title based on the engineering innovation for the hydrogen productions. Okay. So this today we'll discuss some better or skilling to you, sharing to you. This based on the working process hydrogen productions already general flow. Okay, so these all are you can telling the general flow. This based on you can use it the here energy input, gas separation and the compression and the storage, hydrogen generation and end use. Okay, so this all are you can use it the general flow. Okay, so here you can use it the here energy input means you can utilize the electricity only. Okay, so that based on you can see the here solar or wind or grid or hydrogen is supplied, you can use it. And the gas separation means you can use it the here. Hydrogen is purified using the membrane, or you can use it the here pressure and receiving for the absorptions. Okay. So these all are the gas separation you can use it. Next to come to the here compression, or you can telling the here energy storage. This storage you can see there's some storage in tanks, cylindrical or pipelines, or you can converted, you can use it here in ammonia. So somewhat flexible and based on the industrial and you can develop. So come to the another point, hydrogen generation means already that water splitting and steam reforming biomass and conversions, or you can telling the here thermochemical cycles. This all are you can use it the hydrogen generations. Okay, where you can use it. That's called you can telling the here end use. That the fuel cells, transmissions and engines, industrials or grid energy storage. These all are the you can use the some end uses. Okay, next come to the main point of the you can use the method. That method based on the hydrogen production, you can use it here only 5 points. This is the very important the point. That point you can use it here electrolytes. You can use it here green hydrogen. So that's all. You can only electricity. So the photovoltaics that application you can use it. After then water splitting, how you can get it the hydrogen separate and you can use it the here oxygen separate. This based on you can use it the here AEL and PEM and SOE and nowadays you can the AEM. So this based on you can implement it for the year. Our focus here AEM only. We will discuss some my experience sharing here. So this is a very important background. That background based on the SMR already that based on the gray or blue hydrogen production you can use it. And biogas already yesterday IIT professor discussed for the year some implemented for the you can see the here low carbon, how you can reduce the for organic materials. So that based on the heat production, that based on the here some gases how you can get it the here CO and H2 and CH4. This all are the how splitting you can get it. Some already you can get the knowledge. So come to the another point, fourth point, you can see the photocatalytics water splitting. So that's the based on you can see the here use sunlight plus catalytics to split water and still in research stage. So still they are not achieved the world level. You can calculate it, you can survey, you can take. Still we are not get to the correct way and more efficiency still not get. So they are all day by day research we are doing. So we'll get to the 2030. We'll get to our STC goal. if possible 2030 will get into this achievement also. So next to come to the fifth point, you can show thermochemical cycles. You can use it the high temperature cycles, so that based on you can see they get some powder that based on you can interact for our solar energy, or you can nuclear energy, you can involve some more energy, you can get the thermochemical process, you can that also chemical you can get into the hydrogen production. So okay, but that thermochemical cycles is still not good that much more efficiency, but they are doing, but that is a way academic level doing the very difficult some laboratories. So come to the this hydrogen very important and useful for the hydrogen innovation. After if you know understand as per the students and the faculty, you can understand for the what advantages, what disadvantages. This all are based on the hydrogen production. Okay, so you know these advantages. You can my main focus 5 point only: clean energy sources, high energy density, support renewable integration, multiple application, reduce carbon emission. This 5 point very important for the advantage of hydrogen production. This based on the disadvantages, what is that? That you know that's based on the high cost, energy intensive, and so storage challenge, and the infrastructure limitation, and safety concentrate. These all are the nowadays very difficult for the disadvantages. So this is very important. This based on you know based on you can why or you can engineer crucibles. This is very important. The another questions as for engineering, we know that's the what is the important this point. Okay, why you can very highlight you can doing the hydrogens. Okay, it is know that's based on the fundamental role shaping society, driving innovation, and solving global challenge. These all are the very more main focus of the engineering solving the solution. This work you can behind the technical design, they built of the system and the technology and infrastructure that support modern life. Okay, so this all are you can use it the here. Come to the another way, they from clean energy and safety buildings to the medical device and digital communication, yeah, engineering transformation, scientific knowledge to practical and sustainable solution that improve the quality of the life. Okay, so this all are where the journey will start for the year this world where well all industrial or researchers or academics you can doing the year main focus of our quality of the life, this human living the all quality life quality of the life. This purpose only we are doing the day by day warring to the research. Okay, so this is the main focus of the engineering crucibles. This based on the here main focus of the 5 problems. Okay, so that problem you can see the here problem solving for a real world challenge, key drivers of the sustainable development, and builders of modern infrastructure, innovation and technology creation. So these all are 4 very very important for the year our modern life of the style. This style you can see the first point: problem solvers, real world challenge. What how you can challenge you can take the as per the engineering role. This role you can see the here some complex problem and develop for the efficient, cost effective, and innovative solution. This you can the problem you can take care. Then come to the you can see the here another issues you can show for the here clean drinking water and developing renewable energy source systems. Okay, so you can use it the solar energy, that clean energy you can develop, or you can do the here some it is improving the transportation and engineering turn of the challenge into the opportunities. These all are go for the your solving the problems. Then come to the key drivers of the sustainable goal. Okay, this problem where you can achieve for the out of 17, which one is you can achieve, you can get it. So as per the engineering, you can achievement, you can get it the SDG 6, 7, 9, 11, and 13. This five goals you can must you can achieve the your research area based on the green energy productions. Okay, so these all are engineering direction contribute for the sustainable SDG goal, including for the year SDG 6 already you know clean water and sanitation. That's called you can telling the adapt for the water treatment and the pumping system and the desalination. SDG 7 already know affordable and clean energy. That's the solar, wind, hydrogen storage systems. SDG 9 already know that's based on the industry innovation and the infrastructure. Also, you can improve for the your institution. And SDG 11 and 13, that's based on the sustainable cities and climate action, that the low carbon technology, eco designs. These all are you can telling the here based on the sustainable and the green features. Okay, so this is very important. Based on the here builders of the modern infrastructure already, that based on the road, bridge, hospital, energy grid and network and the communication system, this society depend on. Okay, so without engineering, modern civilization cannot function. Already, this based on the third point. Fourth point, you can see the here innovators and technology creators. That's the engineering driving. What you can use it here, how you can develop. Okay, so nowadays the peak came here artificial intelligence. Already, Okay, so any system you can develop for the material science or design or any some ecosystem you can develop, all involving AI. Okay, so this based on the AI and the nanotechnology, renewable energy system, space and aerospace technology, and the biomedical implant and device. These all are you can rising living standard and open new possibilities for the future generations. Okay, so this is a very main backbone of the here engineering crucible technologies. Okay, so after then here that's the based on the our focus here aim is hydrogen production only. This hydrogen production based on you can improve here what you can growth, what where you can journey will start. This based on you can see the here eight type is available for the hydrogen production: gray hydrogen, blue hydrogen, green hydrogen, after then turkish hydrogens, then yellow hydrogens, then white hydrogens, and pink hydrogens, and brown, or you can tell in the black hydrogen. These all are basically you can type of the hydrogen productions. This based on which one is our focus, you can keep using your research area or some crucible you can study in the point. Particularly one you can focus, after then you can research do. That's why you can get it the more achievement, then you can get the good publication and good proposal you can get it. Okay, so my focus here green hydrogen only. This based on the produce through the water electrolytes and the renewable energy based on we will using the solar energy level and zero emission I will reduce, and most of the sustainable and currently more expensive we will saving for the here our green hydrogen productions. Okay, so then only I have selected here solar desalination system. That system you can implement the electrolyzer. How you can generate for the our desalination water you can using, after then water splitting hydrogen, how much you can get it. Some after then I will show it one by one. So this is all generally you can see the here very type of the hydrogen production. This based on I focus here hydrogen production only. So that's based on the green. That green means what? Okay, so what is the meaning of green hydrogen? That you can basically ask for the students and the faculty will understanding all. Green hydrogen means already it is hydrogen produced using the renewable energy source. So like you can use it here solar or wind, or you can hydropower. Anyone you can use it. That based on the your research. Okay, it is created through the clean process called the water electrolyzer, where you can electricity split water and hydrogens and oxygens and without releasing carbon emissions. Okay, so this is the called you can tell in the hydrogen green hydrogens. Okay, so why it is called green? Okay, so that's based on understanding. So entire the production process is 100 clean and does not generate CO2. No fossil fuels. That based on you can say that no pollution and fully sustainable. That's called you can telling the here green. Okay, so how green hydrogen is produced? Okay, so this is a very important. Renewable energy you can use it to the electricity, wind or solar. You can anyone you can use it. That power you can electrolyzer you can use it. That's a positive charge and a negative charge you can connectivity. You can see the here PEM and AM. Okay, so which one is you can alternate, you can get it based on the your research. So this electrolyzer splitting water, hydrogen is collected as a fuels and oxygen is released or used. Okay, so this is very important. Electrolyzer split water, you can see the here HT is collected as a fuel. Okay, Oxygen is released or used. Okay, so this is a very important. Hydrogen is storage in a tank and used to the energy transport and industry. These all are the very useful to you. Okay, so this based on the green hydrogen advantage and disadvantages, what is that? Okay, so advantage you can telling the here green, zero carbon emission, renewable energy and sustainable, high energy densities, can store excess renewable energy. Okay, disadvantage here, what is that? Okay, so that values we can see the here, high production cost and require large renewable infrastructure, storage and transport need special systems. Okay, so this all are disadvantages there. Okay, so this all are the nowadays our government also support some funding call for came. So I think 560 millions funding allotted. So that based on the any research doing the hydrogen, you can approach the DST funding or SERB. You can see the now. I think Kalparke will come. Okay, earlier will come. So if possible, that's a tie of Bombay IIT. So that's a main. They are taken for the IIT main role. That role subsidy gives some private college and some private deemed universities and some applied college. They will some split. They will give the funding 20 lakhs or 30 lakhs or for 50 lakhs or 1 crores, 2 crores. Based on the your approach, your proposal, they will ready to funding. They will give to you. So this based on you can approach. The disadvantage you can overcome. That's what you can overcome. High production cost and require large renewable infrastructure, storage and transport need special system. This anyone based on the not only production, okay, storage and transport. In both or in three, you can achievement, you can writing achieved, and you can writing the proposal. Must we can get the funding proposals. Okay, so if possible, all faculty members or students level also they will give the year with the Utti. Okay, so that's a ANR of philosophies. Several call for games for second year student, B Tech or B engineering, second year students and third year students and fourth year students. You can write and based on the your mentor discuss some new idea you can apply based on the storage, production and storage or production and transportance. Okay, this both multiple you can get it your proposal. You can submit a government sector. After you can get it funding. Okay, so after then funding get it under some achievement you can get it. Your profile is very good sound to you. Okay, so these all are disadvantages you can overcome. This based on you can see the here. I here focus of our material you selecting and after then integrate for the hydrogen material plus solar desalination. What mingle, what mixing, how develop, that only we'll discuss here. So already you know based on the solar desalination how we can generate for the this work integrate for the solar energy system and produce for the both green hydrogen and desalination water. Okay, so that's a saline water you can convert for the engineering innovation. You can security you can get it. This based on the your power water purification and the hydrogen production simultaneously you can generate. This is our aim. That aim based on you can see the here some solar desalination principle already you know they are based on the process you can use it the energy to convert salty or improve water into fresh. That's called you can telling the saline water. This water you can telling the only the human you can use it the get drinkable water. Okay, so that's a very important. This based on the how it works. Sunlight heat saline water, water evaporated leaving salt and impurities behind. The vapor contains as pure distilled water. Okay, so this is the very important the point. That point why it is important. Okay, run on renewable solar energy, provide the fresh water in coastal, dry or remote regions, low operating cost and eco-friendly. These all are the very solar system desalination support for the our sustainable. This based on you can see the here predicate and the predication. You can see the here solar power renewable energy for the future generation. What you can do in the research. Okay, Nowadays, any scholar are not involving, not touching the textbooks. All are going the chat GPT. After then, you can writing and paper publication. What use our societies? Okay. So based on the my suggestion or based on the scientific book and textbook, you can refer. After then, the research what they are done, how you can overcome. That was a research good article you can download and you can read. Then you can achievement. You can go for that's called you can approach here predication and productions. Okay, so predication not there and the production not come. Okay, so nowadays predication only coming but production not coming. Why? So here as per the I am editor, I saw the here our journal for annum 1 lakh above came the research papers, but all papers all ChatGPT content only. On the real content not writing any researches. Okay, what we can do as per the editor? Okay, as per the researchers, not give the any original work. How the editor give the acceptance? So nowadays several paper all reject only. Okay. So why means ChatGPT means they are giving the some ideas, some software, some CSE background, they will software and they are improve for the growth of the life. Okay. So technology they are developing. The technology you can how you can utilize. Okay. What where you can improve. That's a very important your role. Okay. That role based on you can improve for your predication and the production based on the solar power renewable energy for the future generation. Okay, so this picture you can see the here your mentor daily shouting but a scholar and reading and after not understanding. So, okay, day by day going and 4 year for 3 year 5 years gone. After that no ideas, no publication, no product. Okay, after when you can see the see some agencies there, some money you can give. After then publication you can do. After get PhD go for the private sector. Nowadays they are all more torture to you. Okay, so as for the PhD, good quality you can make. Really, you can study after understanding problem solving. Some solution you can get it. After then you can go for the growth of the life. That's all you can telling the here future predication of the solar power. Okay. So after then this based on the predication you can utilize for the some design. That's the eco design you can improve. So society very useful to for the here. That's all you can telling the solar power predication of the stagnates. Okay. So these all are the very important. Already, rapid growth of the 2050, 40 to 50% you can travel 50 terawatts, you can global electricity production, you can get it. This based on the global transition renewable energy, how you can generate. That's a based on, you can see the energy FA improvement and solar energy storage, A and support grids and space based on the solar power. These all are the very important to either you can use the which area you can improve, but based on you can research you can develop. Okay, so here you can see the here solar power production under stagnates. You can use it important future demand and the following the production method to the technologies. Okay, they are you can use it here advanced photovoltaics and floating solar farms and argo voltage and after then solar desalinations. Okay, this based on you can use it here our conclusion here discussing to you primary energy source for the future generation. Then come to the technology innovation and you can improve for the storage solution and the policy supports. This all are you can do. Main focus of the solar energy will ensure yes so sustainable carbon nature feature for the community. Okay, so this all are our aim of our research. This based on basically central solution you can see the renewable energy and non-renewable energy. Already, renewable energy means you can see the here sustainable, eco-friendly, and infinite. So this based on the curriculum source of the energy improve for the growth that based on the sun, wind, and bio, coal, and natural fuels and geothermal. This all are you can improve for the your source of the energy. This all are you can limited and supply for you can use it the pollution and the control and the climate change. That's a non renewable energy you can use it. This all are you can use it the here renewable energy sources. That's a solar energy and wind energy, bio, tidal, and geo energy. All you can utilize. That non-renewable energy already that's a coal, petroleum, electricity, firewood, and straw and tried truck. These all are focus of the your future trend to focus on the solar, wind, and storage technology to ensure that the clean sensor you can use the sustainable power supplies. These all are the very important to the point. This point based on the you can discuss here already. This slide I discussed to you. This based on introduction, So based on here, you can use the solar energy. Some introduction you want to. Okay. So solar power driven for the radiant light and the heat of the sun to stand as the concert stone to the renewable energy sources. This you can use it the global valuability and you can minimal and environmental impact of the during the operations. Okay, so what you can improve the during time operation you can do that level you can go for your ensuring energy securities. Okay, so these all are renewable energy sources. You can go over the energy sectors. Okay, so this solar energy can be harvesting. So you can improve for the through the various technology and categories. Two main focus of the methods. One is photovoltaics, another one is solar thermal methods. Okay, photovoltaics already that's a which direct convert to sunlight into the electricities. Okay, that's called you can telling the photovoltaics methods. Okay, so solar thermal methods that's a which utilized for the solar radiation for heating purpose. Okay, after then you can convert to the electrical mechanical energy converted to the electrical energy. That's called you can telling the solar thermal. This report device you can see the here history of the solar power and explorers you can use the underlying you can technology and the highlight of the emerging advancement to sorting of the feature of this vital renewable energy sectors. Okay, so finally, what they are telling here, all renewable energy sectors only they are improve for the here. This based on this, who is introduced the solar? Already that the history of the solar power. Earlier beginnings 7th century BC, 9th century. You can see that here several scientists is there. So this sunlight you can practically propose can be tracked around the census centuries BC when human used the meanings and the glasses and the concentrated sunlight to the fires. Okay, so this all are you can see the here first incidents. You can see the Greece and Rome. You can solar energy was utilized to the heating buildings using the passive solar design principles. Okay, so this is the first introduced is okay Greece and Rome only first introduced solar history of the solar. And the second one is scientific discoveries and 19th centuries. You can setting the here scientific fundamental. We can see the here solar power is lied in the 19th century, 1839. The you can see the here Becquerel discovery. You can see the photovoltaic effect. Observing the certain material generate an electric current when exposed to the light. Okay, he is the first to introduce the year 1839, like Becquerel. Okay, so he is the very first introduced for the photovoltaics. Okay, so this discovery developed and way of the photovoltaic cell. That's a solar cell. That cell, what next generation we can improve for the year 1873. That's here Smith. Here, what he is telling the year his discovery photo conductivity of selenium, further contributing to the understandings of the light to electricity conversions. Okay, so 1839 is the photovoltaic effect is explained that based on the current how much electricity generate to light. Okay, then 1873 Smith is telling the photo conductivity that also selenium material is used. After then he is telling the here electricity conversion there some point of is done. Okay, so this first solar cell and application led we can tell the 19th earlier 20th century. The 1883 that's a Charles already the scientist. Okay, selenium based on the solar cell, although they had very low efficiency. Okay, so 1883 is telling. After then another scientist came. That's a 1980. Sorry, 1905. That's all already the Albert Edison. He's explained photovoltaics efficient. You can see that here is some scientific proof he is given. After then he's got the Nobel Prize. That's the theoretical basis of the photovoltaics technologies. Okay, So 1954, Bell Laboratories is developed for the first practical silicon solar cell with efficiency of around 6%. Okay, this marked significant milestones in the development of the modern solar PV technology. Okay, earlier application of the solar cell, including the powering space satellites into in the 1950 and 1960. Okay, so this all are development and commercialization and late 20th and 21st centuries. This oil crisis and the 1970s, you can see the here some spotted and renewable industry to the renewable energy sources, including solar. Okay, so this research day by day developing and effort and resulting in improve the solar cell efficiency and reducing the manufacturing cost. Okay, so that finally the 20th and 21 that centuries, that many countries the government sector incentives you can funding allotted for the policy and the technology development and achievement also. They are day by day research and developed, and then solar PV photovoltaics that based on the, you can say, the commercial and utility space application also they are developed. Okay, so come to the emerging technology in the solar power that usually the get some loop, that loop based on the can evolving and with ongoing research and development, improving the efficiency, reducing cost, and expanding the application levels. Okay, so this based on the emerging technology already, you know, the based on the, you can see the here several type is available, that based on you can see the which one is you want, and based on the, you can select and you can do the solar forms. Okay, so after then you can see there's some advanced nowadays doing the quantum dot solar cell, very more popular interact for the nanotechnology and high absorption and efficiency you can get it. That along to the, as per the computer science already I said, that based on the artificial intelligence involving for some optimized energy distribution and grid integrated and predicative and the maintenance for the charging and the recycling and the power batteries, everything they are in that order. Then you can involving for the solar power hydrogen production. They using the solar energy to split water and produce the hydrogen, green hydrogen for the energy storage and transportations. Okay, so this all are the photovoltaics background. This based on the future outlook for the increased efficiency and affordability. Okay, integrate with the energy storage, and you can use it as some material lithium, sulfur, and solid state batteries. While you can use it the IoT based on the microgrid also, you can use it as some triple background. They will use it. The solar technology is developing, and you can improve for the passengers, and you can do the cleaner and more energy independent and with the features. Okay, so these all are the very important. This based on, you can see the here some the synthesis properties based on the as per the engineering mechanical engineering, you can understanding for the some application some properties. If you want some element, you can select the properties you want. After then you want the synthesis materials based on the which technique is suitable to the hydrogen production. Then application back how you can improve the your application. This three part very important to you. This all are you can select based on the suitable material you can select. After then you can select here hydrothermal treatment or in layer by layer assembly, or which one is you want, and based on the, you can select, and or electrochemical or electro spinning. Okay, so the thin film on the spin coating, several techniques there. The techniques which one is you want, and you can develop. Based on the, you can developing for the application level, you can see the here catalyst sensor, or you can see the photo catalysts, which one is you want, based on you can improve, and you can tell the here nano particle or nano composite, or you can see that copper tube, or which one nano copper tube, which one is you want, and you can select and you can develop. This based on the matrix, you can see the here some based on the carbon inside the how you can interact, you can get it. That already know classification of the matrix, that material how you can color select. So that based on, you can see the here carbon and graphene metal matrix materials, metal matrix materials, ceramics matrix materials, polymer matrix. These four element only based on the material matrix available, that which one is you can, if you want, and you can select, and you can growth, you can do. Okay, so you can do the here two or more spaces, matrix spaces, you can select. After then you can tell it here composites. Two or more spaces you can involving for the matrix space, that called you can telling the composites. Okay, so this composites based on the, you can see the here any material, you can see the here composite, that polymer material, you can see the here thermoset material and thermoplastic materials. Okay, so that material several is that, that material based on you can see. Okay, the composite material, you can see the here particle refine force and the fiber refine force and the structural. These all are 3 point very important. These all are you can tell in the type of the composites. Okay, so after them this composite, how you can fabrication you can develop. Okay, so this based on the techniques and which one is you want the techniques you can utilize. Then based on the your low cost and material, based on which techniques adapt that material, how much you can growth of the your crystalline, that you can develop in the here solvent hostings, or you can use it the here gas forming, or you can use it the 3D printing, based on the your aim of the element and scope of the research. Okay, come to the here another focus of the sustainable materials for energy conversion and storage. This energy conversion storage, you can see the here called natural sources only. That's called you can tell in the environmental predications. Okay, so that the predications you can improve for the energy conservation. You know the here thermal energy, electrical energy, nuclear energy, electromagnetic energy, mechanical energy, chemical energy, sound energy, etc. Okay, so this all you can improve which energy you research based on you can use it and you can develop it. Okay, so here we can use it the here all thermal energy, that mechanical energy also we are interact, and after then we will growth of the our energy conversion. Okay, so you know that's based on the natural resource and environmental predication, that is called you can tell in the here wood and bamboo and other plant based on the material sustainable, because they are growth of the natural aluminum, copper, and other metals recycle identified. Okay, so these all are the very important. This paper you can improve for the this work. It is related to the produced or based on your nature fibers only. Okay, so that's called you can sustainable building materials and inbuilt craft steel and recycled plastics materials. Okay, nowadays we are working very more all sustainable materials only. Okay, so this energy conversion and storage, you can use it here transformation of the energy by the nature for the form of the used by the human. Already naturally, as per the engineering, you can discuss here. You can weekly, daily, you can use it the two-wheeler or four-wheeler or six-wheeler. That's based on you want here batteries and fuel cells and large scale of the storage energy. These all are as per the engineering. You can go for the challenge of the storing and transmitting renewable energy of the electric grid. Okay, so these all are the very important to you. So finally, you can see in the here chemical energy. You can convert to energy to form of the work. Okay, so this is a very important. This based on you can see the here which one is if want, and you can see the here. So based on the development and the new material and the solar energy conversion, you can use it the here some basic you want. Okay, so here basic surveys, you can see the here you can telling the electron spinning. Okay, so Bohr atom structure, what inside the you can bond van der Waals bond structure you can get it. That based on the you can see the here Einstein E equal to mc square, how much you can energy you can get it. This all are you can making, that's called you can your atom, how much your efficiency you can get it. So that's some calculation is that, some protocol is that, that protocol you can see the here solar to chemical energy conversion for the generation of high energy chemicals is the one of the most visible solution for the used for the sustainable energy sources. Okay, so you know that's based on the rainbow, that's the seven color is there already, you know, based on you can see the here red blue, that's the science color, and yellow color you can telling the engineering color. Okay, so any product eco design, any product you can take it your prototype, three color mingled, then only you can hi-fi you can get it the any one white lights. Okay, so this white light some range is there, that range you can telling the 350 nanometer to 700 nanometer. In between, which one is your nanoparticle, how much you can achieve into the electro radiation sun rays, how much that radiation thickness density you can get it, that based on only your material very quality you can get it, that very long life you can get it. This based on you can see the here very product type. Okay, so some experimental you can see the here our lab you can see the here our electron spinning, you will get it the here synthesis of material. So in between the stirring, after then some boiling, you can get some methods. The electro spinning method you can see the here. After then our some heat will come, that chemical interaction. After then that inside that all electron spinning will get it. Okay, so this based on the you can picture, you can see the here inside the spinning that particles all rotating. That's called nature vibration. That vibration you can see the here one electron, how much stability you can get it, how much free energy you can get it. That's a semiconductor you can telling. That's a you can telling the here valence band to conduction band, how much your band energy you can get it. That energy you can calculate it here valence band to conduction band, how much you can get it the your particle your strength. Okay, so this is a very important. This based on you can see the here sunlight new material, how you can select it. These all are based on the natural phenomenon, and you can use the energy place and every moment to light waves on lower or higher energy to you can, or you can tell in the same amplitudes. Okay, the optical interference or you can light interference you can tell in. These all are you can see the here some chemical material, you can see the here 7 colors you can attract. Then based on the your argo material, that material inside the, you can see the some nutrient ring you can get it. That nutrient rings means that's based on the 10,000 million is available your nutrient rings. That based on the in between you can get it the how much your band will get. That's based on you can take the characterizations or 10 or AFM you can take at the time your values, how much nanometer values you can get it. Okay, so based on the material your vibration you can get it the how much you can get it the vibration. After then how much your band gap get it. Then come to the here inside the saline water, how much evaporation naturally will get it evaporation. This all white color you can tell in the molecules. That molecules you can adapt in the here all three colors, the rain, red, blue, green. These all are very important, the three color. This based on you can see the here water molecules, how much you can interact. Our color you can material, how much you can interact for the molecules. That molecules attract for the here more radiation absorption you can getting the for sunlight. Okay, so basically, sun rays, you can see the here sun rays, you can use it the here two types already, already I said to you, PV and solar thermal. This based on you can implement it for the some classification. So here solar desalination, you can use it the here, how much you can get it. So that integrate for the solar cell, you can use it the silicon and the semiconductor compound and emerging or novel material, you can use it the some solar cell compound. That based on you can see the such a solar cell. This solar you can use it the chemical compound. How you can get it the chemical based on you can interact for the some molecules, you can get it the some reaction. That is a ferrite, and how much you can get it the interact the donor to acceptor, how much you can get it the energy level. That's called you can telling the here your solar desalination to here chemical your material based on the PCM or nanocomposite to interact for the some absorption, how much you can get it. So that's called simple telling you can telling the here chemical energy, how much you can utilize it. That's why you can use it in our design, how much you can get it the high efficiency densities. This based on we are using the reliance in my formula and generate for the you can how much you can optical theories you can involving that based on the parameter, how much you can analysis involved for the water evaporation. These all are the one of the work we are published. Then come to the domestics. You can use the solar thermal techniques. You can know several 11 type is available. That among this we are focus of only solar desalination only. Okay, so that's called you can telling me here sustainable alternative to fossil fuel, reducing carbon footprints and multiple sectors we are improve our solar technologies. Okay, so these all are the your donor and acceptors. You can improve the some ferrite inside the energy gap, valence band to conduct band. You can some electron how much times is the living. So this based on the calculate E equal to h mu. That's why you can de Broglie wavelength function. How much you can black theory you can observe in black surface area. How much our energy you can boson energy you can get it. This based on you can L equal to Km integral L E lambda and V lambda and D del lambda. That's a fluorescence resonance energy transference you can tell. That's the Raman spectro studies you can take. That calculation you can take that energy levels. Okay, so based on some photosynthesis you can do the Hargo material. That based on that's a chemical energy is a storage form of the sugar cane. Okay, so that sugar cane how you can reduce the credit water and carbon dioxide. Okay, so that's a key man our body how much interact for the some basic formula. This formula Based on you can interact for the activated carbon, how you can electron spinning you can get it. Already based on you can see the here that's the activated carbon means you can the porosity is very more you want. That's called you can see the here low oxygen environment volume porous 500 to 1000 meters square by grams. Okay, so that's all. Absorption carbon is non-polar, or you can tell him the chemical reactions. Okay, so that reaction based on you can see the here three function. One is you can telling the porosities, and the another one is you can telling that material based on you can telling the here micro molecular, and based on you can see the four types you can telling the here how much layer you can adopt based on the your materials. Okay, so this is the activated carbon. So finally what you can tell in the here that electron how much is spinning you can get it. After then inside the carbon how much you can porosity they made, that only you consider the mesoporous or microporous. That level you can how much distal you can get it the your organic material or inorganic material. Based on you can calculate it, some small area organics molecules you can get it. So this is very important. This based on the activated carbon you can some type is there. That type you can calculate it the here. After then we are approach and you can main focus which is we are calculated here powder activated carbon only. So these all are we can achieve for the 95 to 100% you can some latex for crystalline you can get it. This based on the methods. Raw material you can collect after physical activation and carbonation activation and washing. After then you can get the activated carbon. This is one of the way. Another way you can go for the chemical activation. You can see the you can add the mixing chemical agent, or you can see the NaOH or in something. You can 11 you can H3O4 or anything you can add the chemical. After then you can get it the some washing. After drying you can get it the activated carbon. Okay, so or any unnecessary you can add it. After then that environmental our lab is some problem will come. Okay, so this picture you can see here any wrong material you can add it. After then here fire will come. So, okay, after then our eye problem, our body some problem will come. So that's a very important. Okay, so these all are the very back of the physical and chemical phenomenon to transform raw material and how the energy input destroyed and product for the global optimize for the object of the your materials. Okay, so this is a very important. So organ material you can collect, and after then some synthesis material how we can develop for this flow chart. Then come to the here achieved here this we are all this journal is 11.2 in part of chemical engineering. They are achieved for the activated carbon only. Prepared after then solar desalination interact. After then get to the more yield. That paper also last year we get the award. Okay, so this based on the you can achievement that chemical you can add in the activated carbon that using the methane and the hydrogen storage also now introducing for the that work based on the we are working now current working. So this based on the some structure argo material some you can drying. After then you can making after synthetics process you can doing the gear that finally you are getting the activated carbon. After then based on how you can tell you carbon activated carbon you can do some basic on FTR, XRD, AFM, SEM, and this all other some structure you can get it. So based on you will get it here highest volume you can telling the 14.38 to 75 nanometer you can get it. So after then you can get the your values how much volume you can get 83 83.55 porosity values you can get it. That's a value size you can get it. This all are the very important. This based on you can see the activate carbon testings. Okay, which one is how we can tell chemical or electrochemical, or you can which one is you want, and based on you can see the here activated carbon 3-4 types is available. The types which one is you want and you can select it here. So after then classifications and how connect the activated carbon desalination classification you can mixing, and after then integrated how you can efficiency you can modify. Okay, already we are preparing the physical and chemical in both type all fixed. After the activated carbon we are made, and the activated carbon we are black paint and mixing for the basin area coated. That's a solar desalination used it. That solar desalination some paper we are AL and ML also energy protection and reduce the cost also we are analysis. Then come to the point solar desalination two types, on the passive and another one is active. Already passive means naturally evaporation will get it. Active means without a natural source you can evaporation you can get it. So that's a activated solar still. This based on passive our main focus of the passive solar desalination only. So conventional single slope, double slope on the big types in the solar we are working now. So this is a very important point. This based on the point some synthesis process, you can do the activated carbon. So inside the black point and the activated carbon add and more vibration you will get it. So naturally they will blinking and spinning you will get it. Okay. So then only we can get the more yield process you can get it. Okay. Then based on the you are achieved the another work, you can zinc oxide activated carbon. That based on the you can see the here inside water, saline water inside the some splitting you will get it. Okay. So after then that activated carbon, you can see the here 30 nanometer level. You can see the here nanoporous level. You can bond such a very more thin nucleons you will form it. Okay. So that's you can tell in the here. Okay. So this is a very important the point our achievement already. This only one paper published. So come to the point, you can based on you can use it like here PEM and AEM two electrolyzer is that. So that's we are main focus of the AEM electrolyzer only. We are main focus. So this is parameters and electrolyzer PM and AEM. So okay, so this based on we are improve on the basic technology. We'll get it. Our aim is we are low cost and scalable and membrane stability under development. Okay, so some very high level you will get it the based on now we are working now here AEM only. That's called anion exchange membrane only. So that's a Ni material here lithium RU in both mixing and we are developing one prototype so that I will show it. So after then you can see that here PEM and AEM organism based on suitable materials. Okay, so that suitable material which material based on you can select which material. This is the main focus of the materials. Okay, so PEM you can select this is a very main focus material. AEM you can select it this only very main focus materials. Okay, so any you can select after then you can doping material or you can use it here or you or something material which material is suitable to you your application based on you can develop here. This is very important the point. Okay, these all are the that range based on the material. So come to the point today we will discuss for the we achieved our lab. We can ruthenium and nickel. Okay, so nano catalysts this enhanced hydrogen production and anion electrolyzer with solar desalinations. So we are using the three work. One is activated carbon, another one is AEM, and another one is desalination. Three work multiple we are working now. So now prototype also we are done here. Okay, so we come to the point here. We selected the here using the thermodynamics analysis upcoming recycle material. That's recycle materials you can use it the sugar cane. Okay, so the sugar cane back gases you can use it here the ruthenium and nickel nanocatalysts. This you can use it here. It is enhanced hydrogen evaluation in anion exchange. That's the AEM. That electrolytes we are used here. Okay. So this based on the you can see implemented for the your hydrogen oxidation and reactions. Okay. So already you know that's based on the OER and HOR. Okay. So that the two method you can utilize the positive charge and anion and the cathode. Okay. So then both are improve for the here. Okay. So here you can improve for your absorption hydrogen coating that carbon monoxide based on you can oxygen contain species. Okay, so this our aim. You can research our developing here our lab eco-friendly approach for the hydrogen production and utilizing the ruthenium nickel nanostructure. Okay, and activated carbon sourced from the sugar cane. Okay, so that's called we can telling the sugar cane based on the material synthesis. You can see the here that material based on you can improve and then you can get it the values. Okay, that values you can how you can generate how you can based on some basic rule the thermodynamics process we have calculated. Okay, so that's called thermodynamics assessment evaluated for the absorption isothermal and reaction kinetics and energetics efficiencies and ruthenium the nickel nano catalyst. This based on you can see the some material you can prepare. Okay, so this is very important. This based on you can see the here that material I am telling here now title explanation I am giving here. Okay, so this based on the material based on your how you can get at the hydrogen productions. Okay, so this based on the some material based on the electrolytes, some calculations, some measurement, that based on the XPS verifications, then come optical outcome, how much you can get it, that different ratios, that ratios based on the how much efficiency will achievement. Okay, so overall that efficiency 1.71 percentage you will get it the methodology, that based on the hydrogen generation you will get it. Okay, so this is the very important point. That point based on you can see the here that the technical wise, that aim of the our work, you can that roles, that roles you can see the here based on you can see the here some materials. Some materials means you can see the here sugarcane bagasse, you can see the here washed and dried and some brand you can get it. After then some powder you can modify it, that is some raw material you can collect it. Then you can see the again you can magnetic stirrer you can use it, that based on the lithium methyl materials and water synthesis and dissolving and sodium alginates. Okay, so 1 gram you are taken in the 100 ml water distilled water using for the our desalination water. That water under mechanical properties you can analysis for the 120 minutes, that it is ensure that you can complete for the polymer softening. Then you can use it here 60 milligram you can use the lithium chloride, that based on lithium chloride and nickel chloride, you can use it the H2 water, and based on you can 100 ml you can distilled water you can adding. After then you can sonic cutter you can 10 minutes you are 10 minutes you are made. Then you can use it the here that water after mixing under for the continuous stirring, you can use it the 24 hours. Okay, so this based on you can see the some crossing linking and hydrogen gel formation you can get it after 24 hours. Then you can releasing the some gel, you can use it the washing and throw the that's a distilled water you can use it the here free dried up to 48 hours. Okay, so this after then you can use the carbonation was carried out 70 degrees Celsius for 3 hours. Then come to the you can nitrogens with the heating rate of the 5 degree Celsius with minutes, you can time also we are mentioned. Then you can use it the here that lithium nickel material was dried after then 0.1 moles and used in the HNO. Then you can use it that use it after then that the time will taken 2 hours up to remove for the residual impurities. This it is followed by the replicated and you can use it that material washing to achieving a natural pH values. Okay, so these all are the very important to the pictures. These pictures after then you can get it the here some powder you can get it the sugarcane powder you can get it this this. Okay, next come to you can see my here, this is based on you can see the here that material you can use it the here sugarcane material after then some carbon rich char. Okay, how we can get it the activated carbon. Okay, so that's you can involving for the activated carbon was prepared sugarcane based on the material. That material you can use it the here some Bannatyne clay. Okay, so Bannatyne clay means you can telling the some red color and some brown colors. Okay, so this material you can get it the activated carbon full washed after then solar dried. Okay, so again you can hot air one you can get it. Then ground you can set it the here sealed you can get it the here 80 missiles. Okay, so this based on the delighting after then you can get it the some water performed you can get it the under what you can similarly washing and grinding and drying, that based on the material you can predicate it for the activated carbon. Some for some temperature we are made, that's called you can telling the here 650 degrees Celsius we are made it. After then under oxygen and limited and condition for to form of the char. Okay, then come to the you can use the some chemical and activated using for the some KOH, that material you can thoroughly wash it offer to obtain the high surface area get it the activated carbon stable for the absorption and the electrolytes and the application we are using. Okay, so this is all the material process. This material process, after then you can see the here some material, you can see the here some preparation of the RNAC, that's called, you can tell in the lithium nickel activated carbon, that's a sugarcane activated carbon means sugarcane materials. Okay, so this is a synthesis process. So that process already, that we are made for the composite material, that's called, you can telling the here RNAC. This it is synthesized via salt gel methods. Okay, so that salt gel method and improve after then you can selling the here solvent thermal methods. Okay, so that solvent thermal method you can improve for the some involving mixing 60 milligram of RN material and 60 gram AC materials. Okay, RN material lithium nickel material, lithium nickel material, and AC means sugarcane materials. Okay, in both of 1:1 level we will use it. That's a 60 gram to 60 gram we were added with 200 ml. Okay, we are using the distilled water 200 200 ml water you can use it. Okay, so this based on you can use it the some stirring. You can see the here some adjustment that the magnetic temperature 7 degrees. Okay, transferred to the stillness that you can use it the here material. Then you will get it the here solvo-thermal method. That's the autoclave. You can use it that material. You can autoclave. You can use it the solution. You can under want heating for the 8. You can use it the here 300 Celsius. So different temperature we are analysis, but we are suitable for the 300 degrees Celsius only suitable for us. Okay. So this after then that material you can get to the autoclave. So after then cooling, then solid nano composite materials was gathering properly, cleaning and the ethanol and distilled water and allowing to try the 3 hours. Okay. Then you will get it to get 55 degrees Celsius. We are 3 hours. We are allowing. Then you can procedures, you can use it here RNAC. You can get a good surface area, you can get it. This based on the boosting catalytic activity for the hydrogen production we are generated for the our lab. Okay, so this is a very important our synthesis process. Then come to the process. That process you can see the here. You can use some thermodynamics calculation. Okay, so the thermodynamics calculation you can use it the here that what you can improve for the here or RNAC. Some RNAC means you can see the here that how much concentration focus of the concentration, that's a CF into 102%. That's a 102% level we are calculated. But here SV means volume of the sample, and here FT means distillation and factors. Okay, distillation and factors. Okay, that factor you can see the only RNAC only. Okay, so this based on you can calculate the thermodynamics formula and absorption, how much you can batching, you can experimentally will get it. So, okay, so that's called you can see the IN and the P equation and the PO polar radiation, how much you can get it based on your ethanol and isothermal. That based on you can tell in the here how much radiation you can temperature you can get it based on the resistance, how much you can attract you will get it. Okay, so this interaction will go for the your calculation will done. So that based on you can see the here some formula you can calculate it. So that formula how you can get it the here. So batch experimental you can get it the 0.1 gram. That gram you can RNAC, that calculation you will get it the here absorption record. You can overall formula you can calculate. After then 540 nanometer you can achievement you can get it. That achievement you can see the here about you can electro splitting efficiency you can see the here again we are adding the 0.2 nitrogen you can add it the H2O SO4. That values you can magnets rotating for the 170 speed you can RPM you can get it. That based on the during time you can get it the 300 minutes. Then electrolytes you can get it the some sample you can prepare and you can maintain for the following. You can RNAC in concentration for the here finally your absorption material you can get it the 540 nanometer you can get it. SCOW you can get it based on this calculation, that graph you can get it. Okay, so you can use it the here that based on the material, that material only you can improve that technical. The technical experimental values you can see the here all using the some formula. Okay, so that's the formula qt equal to 1 beta into integration for the alpha beta plus 1 by beta into integration the time. So that based on the time, how many absorption, that's alpha beta values, how much you can absorption, that how much your Maxwell distribution function you can get it t power 1 by 2 plus c, that how much you can concentration you can get it, that values you can integrate it for the values, you can integration of how much 1 minus y equal to Maxwell Boltzmann law belongs to the absorption thermic energy level. This level only you can see the here, that's called you can tell in the here how material electrochemical properties you can. This is some calculation is there. That calculation based on you can see the here reaction and some function you can improve the design. That design improve the some reaction based on the values, alpha beta values you can calculate it. That calculate alpha beta calculate means until the transition is finalized. Okay, so that's attained. After then you can how much you can implement it for the thermodynamics equilibrium state levels. Okay, so that state level how much chemical potential you can occupy for the hydrogen gas, that identical to the across for the grass area. That grass area you can calculate for the alpha and beta only. That alpha beta phase level how much you can generate, you can based on you can analysis that expertly you can do the process that continuous equilibrium pressure. Okay, so main what I am telling that this sir, how much pressure you can get it, that's a hydrogen, how much pressure you can, that's a equilibrium state level you can get it. Okay, so constant is there or stable 1 hour 2 hour 3 hours is there based on the sample, that sample only I am telling the here this slides. Okay, so that's you can telling the here this basically you can see the here PEQ, that's the integration. PEQ means you can tell in the here some important pH2 values at, based on the temperature. Okay, so that's based on the temperature pressure how much you can get it, 1.0 into 10 to the power 5 parcel you can get it. Okay, so this value is pressure only, you know, some formula is there, that formula you can calculate it. Then come to the you can tell in the del S, already you know del S and del H, that's the respect to the entropy and enthalpy based on the hydrogen absorption and your material based on the you can calculate this based on you can see the here some values you can how much you can integrate for the pressure values of the 1000 divided by T. That's called you can calculate it. Entropy level and enthalpy level you can calculate it, how much you can get it the your values that based on the RNAC. Okay, so this bond structure you can get the very long bond structure you can get it. So this is this slide very important, that after then how much you can interact you can get it based on the values. I temperature you can get different temperature you can get it, that's a temperature 1 2 3 given. Okay, temperature 1 is very high and the temperature low is very degrees. Okay, up to here degrees will comes. Okay, so that's just landing you will get it here based on the our EP integration of the pressure and the temperature you can calculate it how much you can get into that values are in it here. Okay, so that's a mechanism you can use it here. This slide you can see that here this is a very important the flow chart of the designs. Okay, so this batch absorptions isothermal studies and you can use it the here conducted for the RNAC material, some concentration and ranging of the values you can 1 to 8 range you can get it the milligram liters. Okay, so that maintain you can observe the fixed loading 0.05 grams per 50 mLs. Okay, this spontaneous you can use it the here that 150 minutes you can control temperature 25 degrees Celsius. Okay, this promote evaluated to the adaptable and you can get it the interaction of the molecules, that absorption you can get it that pH value solution. You can see the here that values here you can use it the here 5 ml you can use it the NaOH values. Okay, to credit for the RNAC absorption you can the electrolyzer but use the help of the absorbents. Okay, so this solution you get to calculate and measurement. So as well as you can use the absorption material worked for the equations, that's called you can selling the here how much removal efficiency get it, that based on you can see the how much you can utilize for the pressure values. Okay, so that it can be used to the absorption efficiency formula is you know that's a you can see the Ca minus Cf, that's a concentration in CL values concentration final values divided by constant values in concentration initial values. Okay, into 100. Okay, multiple you will get it automatically. You can get it that some percentage values. Okay, so this is a very important. This based on you can see the some flow chart and you can get it the design. After then you can see the here this material inside the green color is the electron interaction for the here values. After then here maroon color is you can see the here electron interactions. Okay, so here this green color only your hydrogen production form it. After then here A and N is you can see the oxidation formings. Okay, so anode and cathode you can telling the here we are focused only positive charge only anode only, that's called AEM. Okay, so that AE method, this is a methods. This methods based on how much you can oxidation get it, how much hydrogen can produce. Okay, so this methods based on the flow state segment diagram. So this diagram you can see the here some formula is reaction formula is that formula already how you can calculate it, how you can generate it based on the formula and interact for the here reaction for the electrolyzer. That the electrolyzer you can see the HEF for how much you can get it based on the oxidation, how much you can get this formula H2O. Liquid formula you can get the gas and how much you can get it. That formula you can QH equal to QW into 1244. Okay, so this formula generally you can see the here that formula production for the is this. Okay, so these all are our prototypes made in our research lab. So we are our head of the department opened it the prototype. That's here our BTech students and the MTech students and PhD scholar both along we are achievement of the prototype different material, and this is the prototype we have made. After then this method we are only production only. Still we are working storage and transport also we are working, but still not a success. We'll achieve as soon as possible. We'll get it the achievement. Okay, so this is a prototype for the AEM hydrogen productions. Then come to the here after then you can see the based on the if you want some proofs. Okay, so that's based on the XRD some material RNAC how much you can get to the values, peak values, how much you can get into the values. That material based on the you can use the AE material how much you can get into the along values. Okay, so that values you can see the here some JD file is achievement is done. That achievement based on you can see the here interact for the XRD curriculums. Okay, so here XRD curriculum already you know D equal to K alpha divided by beta cos theta. Okay, D KHL equal to A divided by root H square plus K square plus L square. This all are you can particle peak values you can get it the Miller indices function. Then the D means you can de Broglie function how much you can get it the values. That's the peak values how much you can get it. How you can calculate it based on the intensities and the angle. Okay, so that's the 2 theta. Okay, so that material we are different material we are prepared RAC, RN and RAANC XRD peak values getting. This is a here already NI and RU green color, yellow color given. That peak values how much we are achievement you can get it RAC and yeah, RA and RANAC. Okay, so these all are the very important. That what here telling that this slide. It is you can use it the here crystalline structure. That's RUNI doped of the activated carbon that successfully for the incorporation you can get it the characterization you can improve for the brand. That brand you can see the here crystal size. That size you can use it the here alloy space. Okay, so this conforming you can effectively doping material that board of the peak values. That values crystalline you can size. That's while you can 0.04 shifting that the peak value adjacent to the lattice concentration you can do the here partial Ni substrate to the negative shift and to the 200. Okay, 200 peaks and we can support to the alloy material formation. Okay, so this peak challenges demonstration you can see the strong metal carbon interaction to the structural modifications. Okay, so it is final you can tell the XRD conformation phase purity and nanoparticles refined for the synthetics you can use the effective for the hydrogen production for the this support for the this graphs. Okay, next come to the here another this pictures what you can see the here this behavior you can use the hydrogen production based on RAAC material you can provide and calculating and properties you can see the surface area and the total porous volume, how much you can quality you can interact for the benefit useful for your hemispherical form porous material, that structure you can involving for the interaction materials. That material based on you can see the here surface area 603.69 meters square by grams. Okay, so that total surface area you can get it the relativity the pressure and the volume you can get it the area of the porous dimensions and the range of the values you can see the here 4 to 20 nanometers you can get its achievements. Okay, so this is very important, this calculation for the absorption and the desorptions. Okay, so after then you can see the here this pictures what he is telling the here some total surface area, total porous volume area, you can benefit you utilizing for that material, how much you can improve for that designs. That's called you can tell in the hydrogen oxidation reaction, how much you can pressure, you can get to the microporous or mesoporous. That in both of characterization you can analysis here. That's called you can see the here porous networks. Okay, that network you can use it here. Some material you can key structural you can use in the here this picture, that's called you can see the here diameter diameter of the porous and dv values, that values you can see the here based on the xps relevant only. Okay, so you can see the here that material based on the uh, lithium and nickel, based on the how much you can interact you can get it the values. Ruthenium you can get it the values average electron you can get it the some peak values and 11 peak values you can get it. Okay, so this values only you can observe the more layer by layer settle for the AIM absorption material. Okay, again come to the here binding energy, how you can get it the, that values, that binding values you can get it the some porous material, how much you can get it interact for the scenario. That's why you can see there's some Ni and oxygen and Ru and AC material you can very more you can get it that values. Okay, so after come to the here binding energy intensities, how much you can get it the values, that based on you can see the chemical state and the ruthenium and the revolving and information for the oxidation state, electronics modification and the system, that system you can use it here. Some chemical you can co-doping that material, how much the lithium and the carbon. Okay, so these carbon materials, that carbon materials you can use it the some reaction you can use the ruthenium material based on you can 3D spectrum you can utilizing for the Ru material, how much you can electron voltage you can adapt. Okay, so Ru material 280.45 electron volts and the 3D 552. Okay, and you can do the ruthenium 4 plus you can get in the 281 440, that's the electron voltage 3D 552. This model you can achieve the here all you can do the here RANA you can interact for the 3D 52. In this signal expert for the values you can 0.05, that the electron voltage decreases for the binding energy related to the RA materials. Okay, so this is this graph you can explain. Then come to the here another pictures you can see the here that nickel material, how much you can interact for the here binding energy and in the intensities. Okay, so this based on the 0.32 electrons you can interact for the nickel and ruthenium material and interact for the activated carbon, and XPS you can increase the there's some values here. Getting the here you can get the 856 some peak values you can get it the Ni 2p and here 3 by 2. Okay, so this is the Ni 4 you can get it the values. Okay, some values you can see the here some material high resolution you can see the here 10 images, that material you can see the here some 6.02 nanometer to rm material you can achievement you can see the 8.440 nanometers, that nanoparticle investigation you can do the some particle size. So surrounding you can see the here standard quality about 4.48 nanometer carbon substrate you can get it. Then some material you can use the same image, what you can improve the here, that values you can see the here high values you can get to the lattice fringe. Okay, so that the corresponding to the 100 and 101 crystallography phases and interplanar spacing, 0.229 nanometer and 0.204 nanometer, but adapting for the some response for the particles. That particle you can see the here bulk RU, you can cooperate and you can get it the here Ni and support and very intact for the activated carbon. So this all are you can see the here HRTM what you can interact here penetrating that's more point defecting and stemming and patterned strain and increased during the gradation of the alloy material. That's a very important. The alloy material, how you can patterning and inbuilding, how you can molding, you can. That's a very important to you. Okay. This based on the high density of this defect, based on the function, that function you can supplementary, you can improve for the active slides and potentially and accumulating and you can do the electrolysis and efficiency you can go for the AEM. Okay, that AEM only you can improve these patterns only. Okay, so come to the here another point you can see the here some reaction you can see the here RAAC 10 that percentage calculated the particle size how much you can get it based on you can see the here 3 point only very high particle size nanometer very get 4.48 nanometer very high particle size you can get it. Among you can that material RU, NI and AC and where is a seating place you can get it the our materials. Okay, so that's called you can tell the ADAX characterization also done. The ADAX calculation ruthenium nickel activated carbon and oxygen constructed for the plus RNAC. This composite material you can use it the main focus of the corresponding to the successfully nano ruthenium nanoparticles and here nano layered and artificial article structure you can improve for the our alloy material. That alloy material you can get it the nickel you can forming and uniform or ununiform you can confirm the ADAX quality and the quantity of the particles metal and 11.9 corresponding to the 9.2 weightage only we can get it the percentage molecules. That's the ruthenium and the Ni you can get it the 4.3 ruthenium and lithium 4.2. These all are modification. After then you can get the ADAX function. Okay, so come to the another this slide you can see the here some reaction you can some pictures you can see the here this graph EIR free and J. Okay, so what meaning is you can tell in the here you can interact for the some correlation methods. That's the correct or not. Some analysis you can do the directly linking for the catalyst and overlapping and you can structure. You can improve for the some spectral arrangement. Okay, that arrangement based on the synthesis material and methods and homogenesis and you can see the some metal composite material some active or non-active that reaction you can calculate it some characterization is there that's called you can see the here ER free. Okay, so that you can use it the here the activated carbon that mixing electrolytes performance how much you can get it the here region of the quality hydrogen production of the parameters. Okay, so this is very important the point. So this is very important. So based on the you can see the ruthenium material and nickel material along blended activated carbon, how much you can interact for the here, how much you can get the equilibrium setting. Okay, so that values also you can generate for the that's called you can see the here voltmetry. Okay, so this voltmetry you can calculate it for the here some values. What you can telling the here some promised materials that material you can improve the reaction and you can come calculated you can see the here some finally you can get the 11.9 determined as a catalyst we can use it the here some 650 degrees Celsius only very more efficiency we can get it that values. Okay, so this is very important the point that point this slide based on you can see the here some electrolytes here only we are sorted the electrolytes. So electrolytes, you can see the here some efficiency values, how much you can get it the reaction function. That values you can see the here, this common operation you can do the some platform. That material RNAC, that material based on you can see the here some delivering kinetic current density 1.6 ampere you can get it. Then you can get it the ruthenium 50 millivolt you can over potential you can overlap you can get it. Then based on you can see the here approximately that time 2.6 times higher than 0.6 ampere per milligram of the platinum achieved carbon for the platinum activated carbon. What I am telling here, platinum carbon platinum activated carbon mixing, after then you can get ruthenium carbon, you can both of comparison, we have achieved the here 2.6 times higher than platinum carbons. Okay, so this is a very important point. That point, based on the comparison, you can do the here some lower material low cost, based on you can see the pieces activities of 100.2 amperes per dollars. This validity you can separate, you can see the here 17.9 amperes per dollar, you can get it the here ruthenium activated carbon based on the RNAC. This material you can see the here using the increases in current density began 0.375 voltage, that values you can surrounding the you can get it the initial decline between 0.095 to 0.375, in between we are getting the more achievement values. This electronics properties you can in compressing you can do the activated carbon doing the overall efficiency that the electrolytes infect of the catalyst materials. Okay, so this based on you can see the here electro comparison studies, and you can see the here some values how much you can attract for the your values. Okay, so you can get it the RNAC, you can get it the 61% you can original mass activities JOM, and after then you can see the here outcome outperforming you can tell it the platinum activated carbon, you can ruthenium activated carbon, platinum carbon 30%, but ruthenium carbon materials 56% we are achieved the this groups. Then come to the here you can use it the here some 10 and edx you can reaction you can get it the here all energy how much IR free and how much you can get it the J values, that based on you can see the here that in frequency ZX values you can compression you can get the overall set the new benchmark you can alkane hydrogen alkane hydrogen oxidation reaction, whether it's called HOR, that catalysts making the highly promising candidate for the various of the real world applications for this materials. Okay, so you can comparison of the your material. So this based on you can see the here nano carbon material that you use on the you can see the distributions to support the characterization and material internal structure and compressed latex French, and you can conform to the frame of the material based on the sim and analysis of the thermodynamics process. Our material ruthenium and nickel activated carbon, you get to the 7.6 weightage, and we get to the more quality and comfortable for the more efficiency. We can get it the very useful for the our society purpose for the present work. This using for the that material. Next, this slide you can discuss for the hydrogen for the CO formation. Okay, so that CO how much you can formation you can get it. This based on you can see the here under challenging condition 0.1 electron over potential with the 5% CO present. Okay, RNAC impressively and refined the 43% it is initially actively, and after 37 seconds this performance you can see the here we held on the 12% you can get into the activity. Then RU activated carbon which retained 31%. Okay, so you can see the here different RU platinum material you can get to the 13%. After then our RNAC material 44% you can set. So this is here you are stopping CO levels. Okay, some calculation is there, that's calculation based on the this materials. Okay, some you can use it here some electrical potential values. Okay, so that we can apply to that after then how much you can particle you can get to the RNAC values and PTA values, RUA values. This is some comparison. after 25 voltage PTAC, and RU you can get it the 0.16 voltage, and after then you can get it the RE material, you can get it the 0.13 percentage. Okay. So the alarm you can use the some simultaneously you can use the some other calculation is the 0.18 REAC and 0.18 PTAC and 0.455 based on the RUAC material your calculation and absorption you can do. So based on the your intensities binding energy, you can improve the some reaction of the material. So along this proof, you can achieve for the our RA materials very good quality achievement. You can do the based on the comparison platinum material to ruthenium material is very high density you can produce. Okay, so this material all we can use it the solar desalination water purification only. Our desalination water purification only we are using the AA methods. Okay, so this is a single slope solar desalination system. You can use it the here at the internal how much you can boiling you can get it. Some same RNAC material only we are coated in basin area. After then here more energy also absorption you can get it. After then the water boiling very fast you can get it to the here this way. Okay, so this values based on our lab you can achievement you can get the some videos. This is a solar desalination videos. So this is a water desalination naturally will get it. That based on you can see the here how much reaction our design will made. So material inside the some steel material waste material we are inside the keep it basin area we are AN AC coated. After then we are very more temperature we will get it. After then very fast evaporation then we will get it the good what nature water purifications we will get it. 1 second we will get it the 10 drops. Sometimes very fast we will come peak times.
Hello,
Is
sir.
BTech students is achieved these designs. After then
Sir.
BTech for the students.
Hello, sir. Shanmugan, sir.
Yes, sir. Yes, sir.
We have some time constraint, sir.
Yes, sir. Yes, yes, sir. Yes.
Yeah,
Understand.
yeah.
Understand. Sir, just
Okay.
5 minutes, sir. Just 5 minutes.
Yeah. Okay. Okay.
Yes, yes, yes. So every half an hour you'll get it the minimum 350 ml to 40 ml.
From the data like temperature, solar intensity, etc., which includes the prediction accuracy of solar, so irrelevant of the efficient, better and productive.
So this is our prototype for the hydrogen production based on the solar desalination purification water. I can use it here hydrogen. This is our prototype. So based on the some solar radiation ambient temperature we have calculated for the summer and winter. So here starting 8 to evening 5 p.m. So some calculation you can calculate it for the energy conservation momentum energy level. How much the energy saving, how much energy loss. After then, how much is surrounding the temperature all calculated. After then, we can summer and winter calculated. Some throughout the year you can calculate the some energy, how much absorption you can get it. Total amount of how much energy we are saving our designs. This based on you can use it the summer and winter theoretical and experimental values also we are calculated. Then come to the some achievement you can get it. Some finally you can get the how much heat observe the internal heat transfer mode. That based on the how much energy evaporation you can get it. So in summer and winter also we will calculate our based on we can get it the here summer we will get it the here 250 ml and sorry summer we will get it the here the 270 ml and winter we will get it the here 230 ml. So every half an hour we will calculate totally how much water we can get it. We are distilled water you can calculate it. This based on the mass distilled water you can get it. This achievement you can get it the every half an hour. Peak times only very highest you can 350 ml will get it the this designs. So summer also summer and winter also some equal values you can get it. Some efficiency overall efficiency you can calculate it totally 59% you will get it the overall our single slope single descents in summer and winter also equal efficiency will get it. Finally, here you can use it the RANA material. You can use it the here lithium nickel and activated carbon. Very useful to the very low cost and very high efficiency. Will get it the naturally. You can get it the environmental adaptable and sustainable goal also. You can 6, 7, and 13. You will achieve the our this war. This based on the material. You can very high mass activity. Will get it the here 526 Armstrong and lithium material based on the platinum comparison for the materials that activate you can use it the here 0.375 volt you can get it the here more values XPS values that binding you can use it the hydrogen production based on the RNAC nanocomposite material increase the amount of distilled liter and 5 liters you will get it the per day and efficiency 42% overall 42% you will get it. There is some mathematical model and solar desalination maintained for some better operation for the condition for the this nanocomposite material and the designs also. So these all are the our international collaborations. So after then national collaboration. So now currently we are working some discussions in the NIT, IIT, some government sectors and private sector. We are my friends all discussing some this achievement all our collaborate only given the ideas, some support, finance supports, some ideas, some characterization supports. All they are giving internal and international. Some recently we are published the publication this based on the hydrogen production based on the journals. So these all are the working or the our UG, PG and PhD scholar working based on the here hydrogen production and solar desalination, single slope, double slope, big type materials, several type with thermal application also they are doing. So material and material science also doing and in design also some guys doing. So these all are the achievement or this paper will get to the World 2023 will get to the award. So this is our full-time scholars. So one scholar achieved the UGC fellowships. So some PG students get the outside go outside went and the conference will get the prize and he is the best first prize he got the award. So this is our universities open the PhD and MSc. So this is our colleagues working the our friends. So these all are the full-time and part-time scholars. So last 5 years, I got the top 2% for the Stanford universities. So some awards. So thank you. So any question, please ask for me.
Thank you very much, sir,
Sir?
for your session. It's very nice and informative session for us.
Yes, thank you, sir. Thank you.
Yes, yes. Now, from audience, if you want to ask any question, you are free to ask. Any question from participants? Sir, I have one question regarding the solar desalination. As the name of the topic is solar desalination for hydrogen production, something like
Yes.
that.
Yes,
how
sir.
we can integrate the solar powered unit with water electrolysis?
Yes, sir.
Because
Yes, sir. Yes, sir. Yes, sir. That's a good question, sir. So based on the design, you can make, sir. For example, single slope or double slope or big type. That output it will come. That output means the water purification. Naturally, you can get it. That water directly you can connect to the hydrogen production based on the PEM or AEM. Which one is the design you can select directly? That water you can connect desalination output that little you can connectivity AEM or PM. After then you can internal process you can get it automatically. You can get it. There's some hydrogen production bubbles you can get it. So that's a production process. So now we are trying the storage process also. We are trying, so that we are trying, but it's 2-3 times fail came. So again we are working on it, but still we are not achievement to get it. If possible, we also will achieve it within a few years, short times, we will get it that achievement also. That error where is there, we don't know. So that's why we are some good collaborator and good researchers we are discussing, but they are given to the some suggestions. But experimentally we modified, but unfortunately our side any mistake is there or not, we don't know. So that's some correction is there. That correction we are modified. After then, a future will get it definitely.
okay. Whether you are using that active solar steel or passive solar steel for this operation?
Yes, sir. The only passive solar desalination only we are using here, sir. Not active. Only
Okay.
naturally we will get it, sir. Naturally only.
And whether the salinity of water affects the electrolysis process?
Yes, sir. Yes, sir.
कम में
That's
कहाँ मिल रही
that
वो
electrolysis
ये
based on the
225 की
your
आते हैं, फिर हम लोग
Please
उसका पैसा
mute
नहीं लेते हैं, और तो दूसरों को
participants.
बेचते हैं तो वही 500
If you
450
want
ऐसे
to
देते हैं।
ask any question,
हाँ, ले लेना।
sir. Not get, sir, your questions.
Arvind Bhosle.
Sir.
Yes, sir. I am audible.
Yeah, yes, sir. Yes, sir. Now audible. Sir. Now audible. Sometime
whether
before sound came, sir. Sir.
yes, sir. Yes, sir.
Yes, sir.
Whether the
Yes.
salinity affects the production of hydrogen,
No,
salinity
sir.
of
No,
water.
no, no. That still we are working on it, sir. This is the current research. Affect
Okay.
or not, we will verify, sir. We are all analysis going on. So
Okay,
within 1
okay,
year,
fine.
we will analysis that reason is how much drawback came. That drawback will come. That drawback how you can overcome also will analysis going on, sir.
Okay,
So that
okay.
now current research,
Fine,
sir.
sir.
Current research.
Okay,
Yeah,
fine,
yes,
sir. Fine.
yes,
Yeah.
yes.
Any other question from participant? I think, sir, there is no any question from the participant.
Yes, sir.
So
Nowadays all
it
busy,
was
sir. That's
very
some,
nice. Yeah, yeah.
yes,
It is a very nice session and informative session, and we are very glad to have you, sir, with us today.
thank you,
Yeah.
bro, sir. Thank you, bro, sir.
Yes,
Thank
yes.
you.
Yeah, yeah. Okay, you can stop, sir.
Yes, sir. Yes,
I
sir.
think Farooq, sir, is available for the next session. Good morning, sir. Farooq, sir, I am audible.
Yes.
Yeah, yeah, sir. Now, welcome, sir, for the second session of last day of this FDP. It is my privilege to introduce our distinguished expert, Dr. Farooq Khalid, sir, working at IIT Guwahati. Prior to IIT Guwahati, sir had worked at İstinye University, Turkey. He did his postdoctoral from Division of Sustainable Development College of Science and Engineering at Qatar. The key research areas of Sir is applied thermodynamics, hydrogen production using thermochemical cycles and renewables, exergy analysis, sustainable energy, waste management, high temperature electrolysis, nuclear desalination. Sir has received a number of awards like technical consultant for the International Atomic Energy, UOIT Dean Scholarship for Outstanding Academics, Topic Editor at Environment MDPI Journals, Topic Editor at Atmosphere MDPI Journal, has worked as a guest editor in International Journal of Hydrogen Energy. He has received the award of Outstanding Reviewer for the Applied Thermal Engineering Sustainable Energy Technology Assessment and International Journal of Hydrogen Energy. So I welcome sir for this session.
Thank you, Dr. Jatha. It's
Yes,
my
sir.
pleasure. I hope you all are able to hear me.
Yes, sir. Yes, sir.
Okay, fair enough. So thanks for giving this opportunity to be a part of this MDP. Now I would like to share my screen. I think you will be able to see my screen.
Yes, sir. Yes, sir.
Okay, so I can put it in the presentation mode.
Yeah.
Okay, so
Yes,
folks, a very good morning to all. So in the next 1 hour, we try to dwell on something high temperature electrolysis, and would like to see how this is not only meant for steam water electrolysis or high temperature only steam electrolysis, and not only related to membrane and all. So we will go through that how we can take further this concept to membraneless technologies and molten salt and all those things, and what currently we are doing at IIT so that we will see. So that's why I give a name is advancement in high temperature electrolysis for hydrogen production, and not only for hydrogen production we can use this concept high temperature electrolysis for some other value added products. Not only the source, the things will be water, but we can use it for biomass electrolysis, and many other avenues will be open, which are right currently at TRL 1 or 2. But later on in the coming years, those may go up to TRL 5, 6, or 8. We never know. So with this, what is more adopting the renewable energy, so we see a good scope of high temperature electrolysis, because amalgam of both the high temperature as well as electricity. Anyway, so going further into this, so whenever I start my lectures anywhere in the world, I always try to give an idea why we are looking for all those options, alternative options. So the reason primarily can be explained from this equation. As you can see that we are all targeted to reduce the environmental impact of whatever the resources we are using to make out of it. So we all know that this overall environmental impact for a particular country or a nation, or whatever you would like to say, it depends, or primarily is a amalgam of three things. That could be the way you want to add. Either you can add them or multiply them, depends upon you. So it could be population multiplied by how much the consumption you are making and the environmental impact per consumption. So there are the first two things when you look at it, that is population and consumption per person. So those are something that cannot be curtailed down in a, I would say, fortnight. Like for example, population, you cannot curtail it down in a couple of years. It's a long-term strategy which require substantial things. So we don't have a much option to do in that particular site. Now, coming to consumption per person, when we look at it, consumption per person. So when you give an option to broadly classify the world into so-called developed, developing, or growing economies, so what is the main criteria what we look usually? So when you look at the nutshell, I would say the background or whatever you can say that how much the per capita energy a person is using. So when we look at the so-called developed worlds like US and other places of North America, Canada and there, then you will find their consumption per person is much higher compared to what we have in our upcoming or saying growing economies like India and other places. So where the per consumption is quite less. So we say that this is directly related to the progress of the nation because it depends upon how much energy you are using. So how we curtail it down or come to that conclusion, reason is that, for example, there the people may have different kind of gadgets are there. However, in India, those are limited. Like for example, in a typical household, when you look at the US, you will find all those dishwasher is there, and then we will found this oven and many other things are there. However, when you look at in India, typical household, those things are not limited. Like those still are luxury items when you look at it. But there, this is a necessity. So that shows that how the progress can be. So the only option that we left is for the time being is that we can reduce the impact of the resources what we are using. As you look in this graph, there are different resources has been given to you. So it shows a trend from on the left hand side when this lost, you see the emissions from the fossil fuel, and then we move over to the renewables. So which put our case that renewables has a future, and we are, this is a not a very new thing. Everybody knows about it. And then, yeah, it's a quite a interesting fact. And India is doing quite good in that, in renewable, especially in solar. We are doing really, really well in that. However, there are certain challenges in the renewable energy. One is that they are intermittent and fluctuating nature. For example, this is not same throughout the day. Like, for example, intensity varies as you move progress in the day. And then solar is also not available throughout the day. That is another important aspect. So what to do whenever there may be a case whenever you have some time excess electricity, what to do with this excess electricity? Either you have to provide to it to the grid or you have to store it. So in that case, hydrogen can play an important role. So when fundamentally someone asks, is hydrogen a fuel? I would say hydrogen is not fundamentally a fuel, it's an energy carrier. So basically you have energy at one place and then you use hydrogen to carry that energy and transport or whatever you can use it further. So I would like to call it better to be on a safer side as an energy carrier as a hydrogen rather than calling it as a fuel. Yes, it can be used as a fuel for the transportation sector, like in vehicles, hydrogen vehicles. And then where you folks coming from Pune, as we have seen that now there are some companies where they are trying to build this hydrogen three vehicles, three tire vehicles or tuk-tuk or auto rickshaw. So I think the company is coming up. Lakshmikant can dwell more on it. And then the reason being is that it provides you a clean conversion, and if it's only hydrogen, water. We are talking about this only if it is produced from renewable energy sources. And we know that the worldwide still hydrogen is being dominatingly produced or cost effectively is being produced by a method called steam methane reforming. So where what they do is basically they have a methane gas is there, CH4, and then they react with the high temperature steam, and then we produce carbon monoxide, carbon dioxide, and hydrogen, and these things are products have been formed. So this shows that this is a very dirty method to produce hydrogen, but still industry is been using them. Reason being is that because it's a more cost-effective method. So the whole idea about this high temperature electrolysis and molten salt, whatever we learn about in this, is to make this more sustainable, more greener and cleaner. So that is the main idea. We will dwell on that in the coming slides. So when you look clearly at the things about the things, so this is just for the people, those who want to have that, we not only need to look at the system from where the emissions are coming. Like for example, you replace all your IC engines with the so-called hydrogen vehicle or electric vehicle. So what you do is you just shift your paradigm from one place to another. So you're blamed to another part, you just shift that. So until unless you clean your source from where you are getting this electricity or hydrogen, then really you are not going to clean the system, or I would say make it a more sustainable or a cleaner world. So we have to address that source as well. So that's why this 3S technology or 3S, I would say, methodology or terminology, whatever you would like to say, it's a better. So you have to make the source as well clean and sustainable, system as well clean, and the services what you are providing. Like for example, you are having a cooling, heating, and all those will be service. And another figure shows that how the mankind was taking their power. So we know that earlier, when we Stone Age or the age was there, people used to take their energy from the wood. So they burn the wood. Still, some part of the world is still using this wood. And we see that when you burn the wood, it has the higher carbon to hydrogen ratio. So more carbon content is that. So which means this carbon is not good for us, because it not only have environmental impact, but also some health hazards is being observed. So that's why this is one thing. And then this our Prime Minister has addressed this issue in the last decade, and then he has provided this cylinders to all households. So the vision was about that basically, so that at least it significantly improved the health of our other part of the society, that is most important ones, our mothers, our sisters and all. So that help us in doing that part of the thing. So once you have a cleaner kitchen, cleaner healthy things will be there. So this is me. And then coal, oil, natural gas. So these three particular things, when you look at it, they are area specific. Like for example, most of the time in India, although we have a lot of coal, our energy production coming from that. But however, for oil and natural gas, we still import a lot of that from the Middle Eastern world. So we have to rely on them for our energy. So in order to make a nation energy independent or energy secured, we have to switch from such technologies to renewable energy. So that's why this again put our case to a renewable. And when you come to renewable and carbon-free fuels like hydrogen, ammonia, there you will find that the CH ratio is the minimum one. So going further into that, we have heard a lot about hydrogen production. So until unless we crack this down and make it more, I would say, less energy intensive and more competitive, then industry is going to adopt it. So maybe in coming years that could be seen. So the target, as you have heard, I don't know, many of you heard about, so was about Nelson. So 111 was the target. So that was given by, I think, Dr. Mukesh Ambani some time back. So the target was saying that by in the next 10 years, for 1 kg of hydrogen, the production cost will be $1. So that was the thing. So it's a triple Nelson. So you can go and search it out. What actually was it? Okay, so still when you look at this hydrogen, that is typically when you look at it, I'm talking about the production cost. I'm not talking about the selling price. Selling price will be different, as we know that cost production will be different. So when you closely look at it right now, any technology, whatever you are looking at, it may go range from $4 to $5. So we have to bring it down to $1 so that it will be widely adopted by the industries. So there are a lot of methods to produce hydrogens, and each method has some advantages, disadvantages. So this figure shows basically what is the efficiency of those production methods, and what are those. So as you can like these thermolysis or thermochemical cycles, they also have a good option of water thermolysis, 55%, and then electrolysis if you are using PEM, AEM, alkaline electrolysis, or solid oxide electrolysis, they can offer you up to 80-85% of efficiency. And then photolysis, where direct photosynthesis process. So people are also working on that. So it is again a very hot area where people are working, and we are also targeting that area of photosynthesis. But in this lecture, we mainly dwell on thermochemical and electrolysis part. That is, and the other parts we not. So there are lots of methods. So what I'm trying to through this next 40 minutes, I will try to see how we can proceed in this direction a little further. So this is just a combination of showing a pure and a hybrid thermochemical cycle. So whenever you come across this word thermochemical. So what does actually it means? So pure thermochemical is means where you are not applying any electricity. So it runs only on the thermal part. That is thermal energy, or we can say in a layman language, we can say it runs only on heat. So what happened? You have a water molecule. So the primary source of hydrogen production, when you look at it, is water basically. So as I mentioned earlier, we don't have it in a fuel form. So we have it in another form. So hydrogen is abundantly available in nature, and not in pure form, only in other forms like water has been there, or in natural gas, or any other process, or in biomass other we have. So it does not exist as H2. It exists mostly as CH4, maybe C2H6, or maybe other CXXYOH, whatever the other. So primarily this thermochemical cycle, what they do is basically they split this water H2O using couple of chemical reactions, and produce hydrogen on one side and oxygen on another side, and then the rest of these chemical reactions, whatever have been involved, they all are get recycled in the cycle. So it is a multi-step cycle when you look at it. So thermodynamically, when you look at the thermolysis, I would say, of H2O, so you will find that when you want to do split the water, pure water, with the help of electricity. Let's not I'm talking not about electricity, pardon me, with the help of heat when you want to do it. So you can split still this, but you have to apply a heat of around more than 2000 Kelvin. Heat need to be applied for that. Okay, and we are talking about ambient conditions. So the water can split. So this molecule, I would say H2O molecule, will not be thermally stable when you supply that much heat to this. It will split into H2 plus half O2. But in order to get 2000 Kelvin, again, you have to burn some fossil fuel to get it. So there will be no point of using that. However, when you use these thermochemical cycles, so you can reduce this temperature maybe 800, 1200, 1300 degrees Celsius. And when you include this hybrid part of portion of electricity in these cycles, then this temperature can go less than up to 500, 600 or 800 degrees Celsius. So that is the main reason. And how this has been happening, so it's all the thermodynamics behind it. So that is one thing. Now, whenever we are talking about hydrogen production, we should also look into it, how much emissions this any process is making. So that's why it's very important. We have to break down the emissions. So when you look this steam methane reforming method, as you can see here, if you are using steam methane reforming, it can give you 11.98 on an average. However, when you are using copper chlorine or sulfur iodine, these are thermochemical cycles, or I would say hybrid cycles, so which take their energy from nuclear source electricity, and then they have a bunch of reactions of copper chlorine there and sulfur iodine is there, and some temperature is required. So you find that this GWP is less, so which shows put our case that these are really a good option to produce for large scale hydrogen productions. So this is one of the cycles which primarily I have worked a lot on this. So this is a copper chlorine cycle, which is nothing but a bunch of 4 reactions. As you can see here, these are the most reactions were. One is hydrolysis, thermolysis, electrolysis, and drying. And when you do the math of this, all left-hand side and right-hand side, so you will find it out that H2 is finally splitting into H2 plus half O2. That is the thing, and the rest of the things are get recycled in the cycle. So that is the primary idea. So one thing I have make it in red, that is the electrolysis process when you look at it. So I make it red because currently this cycle, what they were using this electrolysis is it in the aqueous phase. So we see that CCl aqueous is there, and then HCl aqueous is there, and then they have to use some membrane in order to separate H2 from HCl aqueous, and then to get it. Otherwise, ions will not pass copper ions and H plus ions. So that was the only thing they have using some membrane to do that. So when you look at closely this reaction, you will find this copper chlorine is nothing but subpowder. Okay, so it's a salt basically, like NaCl or any other salt we have. So copper chlorine is also another salt. So if you want to apply an electricity to a salt, let's say, for example, I have a table salt at my home and I want to apply some electricity to it. Will you notice anything on the anemometer or those things? No, we will not notice anything on that. So no current will pass. The reason being is that because solid cannot do this. However, if you dissolve the same NaCl in water, or this copper chlorine into water, you make an aqueous solution of it. Now the ions are present to transfer the electricity. So you can conduct the electricity. So that's why the reason why they were making is aqueous, CuCl aqueous. So one thing was that. Now, when you closely look at the temperatures, you will find that these reactions are happening at different temperature. So whenever you are doing these kind of things, it will bring a instability into the system. However, you can capture the heat from one stage to another stage, but still this is not exegetically a good idea to do that. So the idea was that why can't we carry out this electrolysis at a high temperature? Now, if you want to carry out this electrolysis at more temperature than 100 degrees Celsius, then you will notice that the water will remain no more of water. It will aqueous and then all the water will evaporate. Nothing will left. So what to do with this? So we come up with different analogy, different strategies. So first was like that. We say that instead of using CuCl and all those things, we will use the CuCl in a liquid state. So we melt the CuCl and then those who may don't know about it, the melting point of the CuCl is somewhere around 450, 460. You can go and check, cross check. I don't remember right now correctly, but it was. So just to be on the safer side, we keep the temperature at 500 degrees Celsius. And then we supply the electricity to it. And then we found that, okay, some copper depositions were there and CuCl2 was observed. And then we close the cycle again with this reaction and we analyze this. So we make it again a thermochemical cycle. And this is the experimental setup which we have used for producing this. So it was a long time back. So the more details about this paper you can find in Energy and Fuels, published in 2018. Okay, so it's one thing we have. So what primarily we are doing is that we make have a high temperature furnace is there in which we put our crucible and then we flow some argon gas into it so that the environment will be an inert environment. And then we have the graphite rods which act as the electrodes. And then first we melt the CuCl up to 500 degrees Celsius, as I mentioned. So we, in order to make sure that temperature what we are requiring has been it. So one thermocouple we put inside the salt so that gives a reading that, okay, now finally we have this temperature has been reached. That's one thing. And after this 500 degrees Celsius temperature is being reached, we switch on our potentiostat and we supply some current to it. And after that, once we supply the current, so this copper chlorine liquid, CuCl liquid, turns into CuCl liquid and some copper depositions were formed. So that was the one thing. However, the challenge or one thing we identify when we were using the previous setup, that the voltage requirement for the electrolysis was on a higher side because it was involving liquid into it. So we say that can we lower down that voltage requirement? So if you really look into that, those who are not from this area maybe. So when I am saying voltage requirement, so I'm talking about an ideal voltage requirement because definitely there will be some losses will be there. So how to identify the voltage in a chemical reaction? So mostly this has been identified with the delta G, that is a Gibbs free energy. So Gibbs free energy is equivalent to the electricity when you look at it to it. So in this cycle, as you can see, the electricity required delta G is 216.7. However, in the previous cycle, it was 251.7. So we see that definitely the electricity required here is less compared to the previous one. So which clearly shows that this cycle is more efficient compared to the previous cycle. So that was the main idea is about. Then similarly, again, to completely shift our electrolysis from the liquid phase to the gaseous phase. So we come up with this idea And we found that when do this, delta G is further reduced. So the whole idea why we are bringing, because when you look at fundamentally, we know that delta G is equal to delta H minus T delta S. So in order to our target in the electrolysis, always to have this delta G as low as possible. That is our target when you look at it closely. So in order to do that, delta H for the reaction remain the same. So the only option is that either you increase the T, because minus T delta S, that is one thing. Another thing is that you reduce, increase the delta S. And we know that gases have more entropy compared to the solids and liquids. So that's what the reason in the gaseous phase, we found that delta G was less compared to what we have in the liquid and the aqueous phase. That was the main idea. So primarily, so it's not something like that. And further, to reduce the number of steps in the cycle from 4 to 3, so we further come up and reduce and combine some step and make it 3. So in a nutshell, when you look at all this 4 cycles, so we found that everyone is whenever someone come to me and ask about something, so I always says that this energy solutions are like drugs. Like for example, whatever the drug we are taking, I'm not talking about the green drugs, I'm talking about the drugs doctor give us to treat symptoms and other things. So energy solutions are like that. So every drug has some side effects. Like for example, in long term, if you take a paracetamol, it will also have some side effects. So similarly, some energy solution, whatever it is, they have some side effects. And another thing is that energy solutions also need to be made very specific. We cannot generalize like that. Like for example, a doctor cannot generalize your prescription. Like for example, two people have the same symptoms, cough, cold, and this, but doctor never give a same prescription to both. Like for example, me and my cousin or whatever it is, they have cough, cold, and this. So it's not like that on my prescription, he and she can go and buy the stuff. That's not the case. So similarly, we have to do for the energy solution. So every energy solution has some pros and cons. So similarly for this 4 cycles, so we were having some pros were there, some cons were there. So when you look at the first cycle, the prawn was a very good prawn. That was that you don't require a membrane for this. Because most of the time when you look at the electrolysis part, the membrane is a bunch of things that has been there, and we are really lacking on that side, membrane stability and so many other things. So the good process with this, if you come up with this scheme one, then you don't require those costly membranes and all those things for that. And then the stability, other things you already been there. And then another one, I would not say it's a disadvantage, a limitation of this process is that the one of the process is a batch process. So why I'm calling it a batch process, because somewhere we have a solids being there, and it's very hard to move the solids compared to liquids and gases when you look at into the integrity, or I would say from an integration point of view. However, that is being addressed by introducing a membrane into the process. Now, once we introduce the membrane into the process, all the processes are become continuous, and that is the one thing. And when we change the phase, we change it low voltage requirement, and again one batch process was there. So similarly, we reduce the cost by further combining this. So that was the whole idea in a nutshell. If you want to have a more detail about this, you can come and we can discuss anytime. So we compare the different proposed schemes all on energy and exergy sides. So we found that the last scheme is outperform the others one and in terms of that. And then we also carried out some techno-economic analysis, and we found that our cycle is competitive to what the other cycle of the world is throughout. Now, one use case I want to show you for the first cycle, as I mentioned that if someone was like that, and then he or she may think that, okay, first cycle is not performing well in terms of efficiency and all, we can throw it out. We don't need that. That's not the case. So we say that, can we make a use case for this? Yes. And then how we make it? We say that we all know that as the renewable energy is going to increase, the share of wind energy is also going to significantly increase, and then the PV and all. So that will lead to, so when people ask me, so I used to say this kind of a thing in my class also, that there were ages like Ice Age, Stone Age, other ages were there. But what age we are looking, we call it, we are looking in a garbage. Okay, so we are creating a tons of garbage is been there. So how to effectively reduce that garbage, or how to get the wealth from that garbage? This is important. So one of the you will find the waste in coming years is the copper wastages will be a lot. These motors and all these wind turbines. So there will be a lot of copper will be there, waste copper. And how to get effectively pure copper from that copper. That is one of the thing is this. So it's a highly energy intensive process. So usually there are two methods what people used in this metallurgical industry. One is they call it as a pyrometallurgical method. Is a other is what with the help of the chemicals they use. So pyrometallurgical is like that. Like for example, you have a copper that has a melting point of around 1300 degrees Celsius. So what they do, they heat this copper to 1500 degrees Celsius. Again, you know that in order to provide 1500 degrees Celsius, a highly energy intensive process. And then the copper got melt, and then the upper layer is the density difference. You produce the whatever the copper bars and other things. You can do that. One thing. Other is that you use a hygromatical process in which they use the chemicals, and there are certain chemicals which has some effect on the environment. Okay, leaching and all those things, and their efficiency is also not that good. So using certain chemicals to treat the copper, and then first put it in this solution, then other solution, and then so many washing this thing. So it will multiple step, and then so many things are there. So that also have some side effects from the environment point of view. So what we suggest to them as one of our alternative was that give this copper to us, so we can give you pure copper out of it, as well as we can produce hydrogen out of it. So it's basically, I would say, hitting two birds with one arrow. That kind of a scenario we have in this kind of situation we can have. So that is what we have studied. We have published such kind of results. So similarly, taking further this thing work from copper waste to aluminum waste. So we have seen there are a lot of aluminum waste has been now generated. We have a lot of aluminum cans and so many other things been there. So I have proposed a cycle that is a 3-step aluminum chloride cycle. So where again these bunch of chemical reactions being there, we have studied this cycle first, its efficiencies and all this theoretically. So first we do the thermodynamics of this, and once we say that the results are thermodynamically coming better, then we think that how to make those processes in a real world. So first process, we have to decide what kind of a reactor we have to use, and then we come up with a solution that we need a fluidized bed reactor to carry it out all this, because our first reaction is nothing but the reaction of a interaction of the solid with the gases. So we have aluminum solid particles were there, like the waste particles. So we have to come up with into certain particle size. We crush them into certain particle size, and then we react it with the hydrochloride gas, HCl gas. And then when this reaction happens, so it will give you AlCl3, that is aluminum chloride, and we got the hydrogen produced from it. So that hydrogen will be of pure nature, having a very good purity. So still right now we are working on that side. And then whatever the AlCl3 we have, we split that AlCl3 again into aluminum, and then we got the pure aluminum from their side. That is the one thing. So these are the different steps we have. So if you are more interested in that, what kind of a reactor we are using, other things. So in our lab, we have such kind of combinations, and we also study the effect of the fluid particles and all those. And then we make for molten salt electrolysis. This is a whole inbuilt reactor we have made, designs and everything from the scratch, and then the electrolysis being carried out. So this is a small setup for hydrochlorination step only. So this reactor we have, and then now we do this analysis, and then we got some results, interesting thing. So that was on the aluminum chloride side. Now we can further used as up to now. I have the first process, that the process that I show in 1920 slides. That process does not require any membrane to carry out the reactions. Okay, so it was a membrane-less high temperature electrolysis, we would say. So which offers a good advantage for us to have. Now, furthermore, we can use this. You might have come across a lot about this solid oxide electrolysis coming into picture, and people are working in that. So in this solid oxide electrolysis, there are two primarily focused people are working. One is oxygen conducting, other is the proton conducting. So that is the main thing. So when we talk about oxygen conducting, like for example, H2O we have, so in that they conduct the oxygen ions. So the membrane allow to pass the oxygen ion, and hydrogen ion will be on the other side. And then that's why we have a split a hydrogen and oxygen from water. Another one are the proton conducting membranes in which they allow the H plus ion to pass. So we know that H plus is proton. So that is the thing. So we are using, and this concept of this studies have been only done thermodynamically. So far we haven't done the experiments on that. So that is our nearby future for that. Coming in coming future, our plan is that. So we think of using this proton conducting membranes for the splitting of HCl. And then theoretically, we have seen that the voltage required in our electrolysis will be quite significantly less if you use at the same conditions, at same temperatures, the steam to split it compared to the HCl. That is one thing. And then further taking this technology for different fuel production. So to now I have discussed about how to have this high temperature electrolysis for your hydrogen production, and then for co-production of from the waste. So one cycle I show you about the copper, other one I show you about the aluminum. Now we all know that hydrogen has another issue that people are challenging or I would say addressing is about storage. How to store this hydrogen, that is another challenge, and people are working on different technologies like metal hydride, converting into another fuels like ammonia, ethanol, so many, dimethyl ether, and many other ways people are working on that. That is another thing. Or compression, some people use the compression, some people use LOCH, that is liquefied hydrogen. So every process has some energy intensive things are there. So our idea was to take this further, this high temperature electrolysis, and see what to deal with this carbon capture, CO2 capture, how to have this. So this is a typical plant in a carbon capture. What happens is that, so they capture the CO2 and they compress it to some temperature, and once you compress, its temperature will rise, and then they cool it further. So this methanol synthesis reactor is certain reactor. The condition thermodynamically, when you look at it, it's a high pressure, low temperature reactor typically. So pressures can be up to in the 30 megapascal, 40 megapascal. So you know that in order to compress the gases to that pressure, it requires a lot of electricity to do that, because these compressors are electrically driven process. So they require a lot of that. So in order to avoid that, can we have an alternative path for that? So we have proposed another technology. So I'm not going into the detail why carbon capture is being required and all those things. So it's a upcoming thing. So people are working on that. So what we say that instead of having this, let's absorb this carbon, whatever you have, into some kind of a salt. We have metal hydroxide salts are there, and then we convert them into it, and then we produce metal carbonates, and those metal carbonates we do the electrolysis, and once we do this, we produce the methanol out of it. And then this is currently VRL, TRL3 and 4. If you're really interested, you can come and show. So we have published one study in the literature about this, and then there are different advantages of this, that we don't require a catalyst for this methanol production from CO2. Otherwise, whatever the process you will see, they are highly require a catalyst and most costly. That so we have, and we observe better solubility. So aqueous will have less solubility compared to if you have a molten salt electrolysis. So this is another step we are using, and then we are working. And we have found our process, when you look at the efficiency wise, our process is 94% exergetic efficient. However, the conventional process is 82%, and energy wise also our process is much better than the other. So this is the product, just to confirm that, okay, what we are claiming, are we really getting or not? So we found that when we do the XRD and all those things, and EDX, SIM image, we found that, okay, what we are converting, we are having that claims are making some reasons or reasonable claims we have. Now that was for taking it this what I am showing you the through this whole MDP. my idea is to give you insight how you can effectively use this molten salt electrolysis for different applications, for different sources you have, and then you can produce different product out of it. So one study we have recently published, it's about the bamboo dust. So since we come from the northeast region in Assam, so in Assam, it's vast land for this bamboo grow. Lots of bamboo is being grown. So earlier, this bamboo was used for paper mills and all, but now it's not been there. So they supply this bamboo to the refineries or other places where they are using this biomass. Basically, bamboo is a kind of a biomass, you can say that. They are using it for power production. So in order to do that, we know that effective combustions of bamboo has to be done. So for that, they require a chip of force 1 inch chip is being required. So they produce these chips from the bamboo, long 1 meter, 2 meter long bamboo. So when you produce this chips, there is a lot of dust is being generated from these machines. Now the target is that what to do with this bamboo dust, because that dust does not have any value. It's just a kind of decomposed or whatever it is. So we say that why not we convert that dust, whatever is being there, into some value added products using our technology. So we take this thermoelectric process, we call it. So it's a two-type one-step process we have, and then we convert it into some value-added products. So the value-added products, again, we have molten salt electrolysis being carried out, and we convert this. And we found that if you do the typical pyrolysis reaction for those dust and our process conversions are much better. We are getting good gases like hydrogen, and then the biofuel we also obtain, and the amount of biochar we obtain is really good compared for that. So that was another thing. Another is that can we use this for methane mitigation? So we have proposed one technology where we say that, okay, so again, a two-step cycle, high temperature things come into picture, and we propose a way how to produce this solar to fuel, effective environment technology we have. So there are different methods direct for this methane conversion. So people use that. However, in our we want to use. So those who are the beginners in this area, because the idea of this is faculty developed program, as people mentioning about it, FDP. So in tier 2, tier 3 colleges mainly. So I suggest you guys to start something fundamentally using some software. So get yourself equipped with certain softwares. So those who are in thermodynamics and mechanical engineering, so they can have either get this HSC chemistry software. It may be a little costly. So if you don't want to go for that, that's fine. There are a lot of the software hop and many other software for man and ERL is available. So get yourself equipped with and give these small projects to your students. And until once you found that, okay, this projects, a couple of projects you give, and you found that this has some potential to carry forward, then you can think about how to take it to the lab scale, or how to get a product out of it, or how to have that. So if you need any support in that kind of thing, I'm always been here. So first think about the novelty, how can bring the novelty into the things, and then how you effectively. So thermodynamics is really a good tool to talk about your feasibility. So first of all, you check for any process what you are trying to do, try to do the thermodynamic analysis of this. And then don't do the only energy analysis, limit yourself, because energy analysis does not talk about the direction of the process. It just give you the quantity. Okay, this is the thing. So I always suggest you do the exergy analysis, and where you will found that when you do the exergy for the processes, and then you will found there are certain processes maybe you are suggesting in your mind, and in which for this exergy destruction will come negative. So such process cannot be feasible. So you cannot go for that. And once you establish that, okay, the process is thermodynamically feasible, then you will go forward to make it, how to make it in a real world, how to make it that. So then the reactor designs and many other things will come into picture. So you can think of that. So similarly, we think of for our this process, how to convert this high temperature electrolysis process into methane to that. So that was our main idea, and then we analyzed, study, and then found our system. So these are the efficiencies we found, and then how much operating voltage of the electrolyzer, temperatures required. So all game is all about the temperature and the electricity. So these are the two important parameters that we always look. So efficiency hardly depend or mostly depend upon these two things. So that is the main important things we can have. So our cycle was much more efficient when we compared the concentrated solar power or waste heat and nuclear reactors. So you can effectively convert that to the conversion process. Then similarly, you can use it for lignin biomass and then for another conversion. So from the biomass, you take the lignin out and then apply this thermochemical process. And then you calculate what is the effect of on hydrogen methanol reductions and then total energy and exergy efficiency of different processes. So we have gone through and then we have found certain results. So effectively, we found that, okay, this is the hydrogen production, this is the methane we found, and we do the analysis. So voltage required is around 1 volt. So that is the main thing. So I think with this, I'm coming to the end of the conclusion of my slide. So I keep last whatever the 5-10 minutes for the discussion. So when you look at it in the nutshell, so I am having here one laboratory that is called as Advanced Clean Energy Systems Laboratory. So we are working on hydrogen and other fuels, high temperature electrolysis, and then e-fuels also. So one area that I didn't cover today in this slide, we are working is basically solar to hydrogen, S2H. So in which we are dealing on low temperature electrolysis like AEM electrolysis, PEM electrolysis, and all those methods. So that is what. And then metal recovery. So from waste copper and all, we are having this. So that's why this is a metal copper. And then we also do the LCA and techno-economic analysis. So to the people, those who want to do some research, so there are some open softwares for LC and all those are there available, and open form also. So I suggest you to better equip yourself with these kind of open softwares are there, and try to give such kind of unique projects to your students. That will be helpful. And if you are having your masters and PhD students, I suggest in the regular coursework, better not to go for the regular exams and other thing. So you can keep this components, project always as a component. So in all my grad courses here at IIT, I teach one course, Advanced Energy Systems. So where I keep this component of the project, and I give it in a group. So we have a student of 20 students, like say 4 or 5 projects I give them. And throughout the semester, they have to work on it. In the class, we discuss half an hour about it in a week, let's say, their presentations and all those things. And out of that, maybe 5 projects, maybe 1 or 2 some really interesting projects comes, and then we dwell and work on it. And last time we also win this All India Energy Hackathon in India Energy Week. We were the runner-up for that, and then students they were the outcome of my course, and we also published some if something is really good on that. So this is how you can keep yourself active. That is what I'm saying. And if you really need any kind of help and support from my side, I'm always been here. So this is just our first interaction. So if you feel any kind of ice breaking anything, please feel free to discuss. This is my email ID. And with this, I would like to thank you all. So thanks, Lakshmikant.
Yes,
And
sir. Thanks
of
a lot.
course, yeah, if anybody has any questions, I'm ready to take it.
Any questions from participants?
Good afternoon, sir. I am Dr. Jnanamurthy. It's a very
Yeah,
nice
please.
presentation. When you go for the high temperature production of hydrogen, what is the kinetic effect will be happening? How it will be splitting of electrons? This is my
So when we have, as you know, that if you have a high temperature, so definitely the kinetics will be much better. So we have done this kind of study there. So as you know that I am from not from a chemical engineering background. I'm from a mechanical engineering background. So we really don't look into, we just look into the thermodynamics, and we know that from the thermodynamics point of view, it's really good to have that. Okay, so kinetics is much better.
Okay.
So our reactions are much more faster.
Okay, sir. Thank you. Thank you.
Sir, which software is mostly useful for LCA analysis? Life cycle.
So yeah. So we are currently using that is SEMA Pro. Okay. But again, it's a costly software to use. So I suggest you can use something freely available, that is Greet. Okay.
Read.
So Greet is there. So you can go and available, use that. Okay. So, but we are using SEMA Pro, and then in the industry also they use two software, Gambi and SEMA Pro are the most, because of their database.
Okay, sir. And sir, is there any difference in high temperature electrolysis and in conventional electrolysis? Only there is a
Yes.
difference of temperature or
No,
anything else?
so it's about the kinetics, as Dr. Ganamurthy was mentioning about it. So kinetics is much faster in high temperature electrolysis, and about the efficiency as well. So these processes are much more efficient. That's the reason we are going for it. Otherwise, there is no point of. And then again, one more thing is that you can couple waste heat to these processes to run out. So it will best effective way of utilization of waste heat. So when you look at the history of these cycles, you will find these are called as a Westinghouse cycle. So it was developed in US in Westinghouse for a nuclear reactor. So to cater the waste heat from a nuclear reactor of that. So mostly these thermochemical cycles were developed that period of time.
Thanks a lot, sir. Yes, any other question from participants?
When you go for the pyrolysis effect, sir, I am Dr. Jnanamurthy, sir. When you
Yeah,
go for
please.
the pyrolysis effect, what is the thermodynamics maximum involved in based on the adiabatic flame temperature or some other way we are find out? Thanks.
So as I mentioned, that pyrolysis is not my cup of tea for that right now. So I am working on something called as a thermoelectropyrolysis process. So what I am mainly looking at the melting point of whatever the thing is that. So first, whatever the substrate I am using, I look at its melting point and I try to keep the temperature just above its melting point, so that I will be able to apply the electricity into it, because the movement of ions will be there.
Okay. Okay, sir. Okay. Thank you, sir.
Yeah.
Hello.
Yes.
Good morning. Am I audible?
Yes, you are audible. Good morning.
Sir, I'm just having one query that why hydrogen engine face challenges in pre-ignition and backfire from thermodynamic perspective.
So as I mentioned, ICE engine is not what currently I am looking at. So I think I am not an appropriate person to ask this.
Yeah. Okay.
Yeah.
Okay, sir. Thank you very much for your session.
Okay.
Yes, sir.
Okay.
Yeah.
So thanks to all,
Sir.
and I really enjoyed. Yeah. Have a
Sir,
good day, and
one
wish
more
you all the
question.
best.
Sir,
Yeah,
just a
please.
minute. Yes, anyone?
Sir, good morning. Good afternoon, sir.
Yeah. Good afternoon.
Sir, suppose if we spraying some solution like liquid solution in front of highly density beam of laser, in the presence of that laser, what about the sprayed droplets, sir? Droplets.
So Mr.
Properties of
Sarvan Kumar. Yeah. So Mr.
yes, sir.
Sarvan Kumar, I think this is not related to what we have talked about, and not to my expertise as well.
Because this is also the thermodynamically involved, the particle undergoes the thermodynamically
So
response,
there
sir.
are a bunch of things in thermodynamics. So I don't claim myself as an expert of a thermodynamic, So I know very little about it. And then rather than giving you a very straight answer right away, I'm not in a position to give an answer right now, unless I understand the problem very well. So I cannot make any opinion on this just right now. Okay, so if you have further things, we may discuss and then we may come up with something.
Oh, okay, sir. Thank you, sir.
Yeah. So I hope everybody has been good with this. So thank you once more, Dr. Lakshmikant.
Yes, sir. Thanks a lot.
So yeah, thank you. Have a good day. Bye bye all.
Bye bye. Participant, we will wait for 5 minutes. Wait for 5 minutes. The next session will start sharp at 12 o'clock. Good afternoon, sir.
Good afternoon, sir.
I am audible?
Yes, sir, you are audible.
Yeah. Yes. You are visible also.
Yeah, thank you, sir.
Yeah. I welcome Dr. Balaji Gule for the third session of the sixth FDP. It is my privilege to introduce today's guest, that is Dr. Balaji Gule. He is the postdoctoral research associate at the Ulsan National Institute of Science and Technology in Ulsan, Republic of Korea. He earned the PhD from SRTM University Nanded in 2021 and working at UNIST since January 2022. His work mainly focuses on the advanced material research, specifically leveraging the techniques like density functional theory and experimental methods for the applications in photochemical, water splitting, zinc ion battery, etc. Recently awarded the prestigious Marie Curie Action Postdoctoral Fellowship by the European Commission and set to join a University of Cork in Ireland in 2026 to continue his research in this field. So I welcome Dr. Balaji Gule sir for this session.
Thank you, sir. Thank you so much for the introduction.
You can share your screen, sir.
Yeah, okay, sir. Thank you so much.
Yeah,
I
yeah.
guess I'll sit.
Yeah. Yes, it is visible.
It is visible. Okay, thank you so much.
Yeah. Just make it in presentation mode.
Yeah.
Yeah. Okay, fine.
Okay. Good afternoon, sir. Good afternoon, everyone. Thank you so much for this opportunity to present my work here in this Atal Online Faculty Development Program 2025-26 held at the Army Institute of Technology, Pune. So today my topic of discussion is about the ab initio and experimental insights into the green hydrogen production via water splitting. So the content of my talk will be like, so first I'll discuss why we are going to deal with this green hydrogen production and all. So the motivation behind this and how the global efforts are there to initiate to increase the production of green hydrogen production and minimize the use of fossil fuels. And then I will discuss about the ab initio method. Especially I will focus on the density functional theory, which is one of the ab initio method. And then I will discuss about the water splitting, how the water splitting works, and how what kind of electrochemical testing we need to produce hydrogen and oxygen parallelly. And finally, I will discuss some case study we have done. So this slide represents the motivation and how the world uses energy and how they gets the energy. So first, the motivation is like we need zero carbon energy carrier. So there is only one zero carbon emission energy carrier, that is green hydrogen. So how we can say it is like zero carbon emission energy carrier? So because so if we use hydrogen production by means of renewable energy, so means without use of any fossil fuel, then the outcome is hydrogen, and which is considered as a green hydrogen because there is no CO2 emission and no other gas emitted. So this is a simple a fuel cell. So you can say so hydrogen and oxygen used together as a fuel, which produces water as outcome, a byproduct and energy. So there is no emission of CO2, so we call it as green energy. So increasingly, we know continuously we are using these fossil fuels, despite we have the renewable energies like we have wind energy, we have solar energy, but these energies cannot give us whatever the energy we demand for what do we say, the industry, the transportation and all the things. So again, we need to decarbonize the key sectors. So key sectors, they include like steel industries, chemical industries. We cannot use here the electrification. Direct electrification cannot be used in the big industries. So we need alternative energy or source of energy to run these industries. Again, there is a need of concerning the global warming. So we know that the United Nations, they have committed to the net zero carbon emission by 2050. So India is also one of the country. So considering this point, so this is one of the motivation. Now, again, the problem is overcoming the cost and efficiency barriers. Actually, we are producing hydrogen already, but it is not the green hydrogen. We produce hydrogen, which is called gray hydrogen and blue hydrogen. In gray hydrogen, we use like natural gas, which produces CO2. So ultimately, we are getting hydrogen, but we are spoiling the environment. In the case of blue hydrogen also, we are using natural gas producing hydrogen, but still CO2 is there. So ultimately, it is not green energy. So the solution is green hydrogen by means of green electricity, and water produces hydrogen, which gives us oxygen as a byproduct. One more thing, we need to consider the intermittency of the renewables. We are using this solar power energy, we are using the wind energy, but these energies are intermittent, they are not continuous. So we need to find a continuous source of energy which can provide us a long-term energy storage and long-term energy supply. So hydrogen is one of the best candidate considering this aspect. Again, we need to enable the hydrogen economy. So we have to find out a particular method or one particular technology to produce efficient and economical water splitting. So currently we are using water splitting technology, which is very high costly. So we need to find a way to make it cheaper and more economical, to make it versatile for the alternative fossil fuels. Again, the main important point is the considering the current situations in the world happening in the world. So enhancing the energy security. So we should be energy independent. We should not depend on any other country for fuels or to make it uh, affordable for us. So like country considering India. So we are also we have also launched the National Green Hydrogen Mission from January 2023. So in that response, NTPC has established his own green hydrogen production plant in southern part of India. And the Atmanirbhar Bharat, the concept introduced by Honorable Shri Narendra Modi ji. So we have to be self-reliant in case of energy. We don't need to depend on other countries in the case of this hydrogen production. That's why. Again, we need innovation in material science to find out better materials to produce green hydrogen. So these are the motivations behind the study we are doing. Now coming to the main topic, what are the ab initio methods? So if you consider, actually the ab initio is a word from the Latin meaning from the beginning and from the first principles. So first principle means the basic or fundamental laws of the sciences, basic sciences. So what are ab initio methods? The class of computational techniques primarily used in quantum chemistry and physics. So these methods primarily involve the Schrodinger equation for the given system. And they use input like the position of atomic nuclei, how many number of electrons are present in the system, and the fundamental physical constants like charge, mass of electron, magnetic moment, the ionic radii, all the physical constants they use to solve the Schrodinger equation. Now, by solving this fundamental equation, these ab initio methods can accurately predict the wide range of properties, including molecular structure, electron density, energies. A different kind of energies can be included here, and the reaction mechanism of different reactions. We can easily estimate. Now, particularly the density functional theory is considered as an initial method as it's rooted in the fundamental principles like quantum mechanics. So what is density functional theory? So density functional theory is widely used quantum mechanical modeling software or code. We can say the software, we can say it as a code, which determines the property of many electron systems by focusing on the ground state electron density as fundamental variable, rather than considering many body wave function. So you should have been a little bit confused with this. So let's see, this is the Schrodinger equation. So we use this Schrodinger equation to find out a wave function and energy of electron at the ground state. Similarly, we can calculate the energy of electron in the first excited state in the second excited state. Similarly, maybe we have studied this the one electron system, two electron system model in our bachelor's and master's in quantum mechanics. But this Schrodinger equation is very much limited as the number of electron increases, because as the number of electron increases, the complexity of the solution increases. So the equation goes on increasing, and it will take a lot of time to solve. So for many electron system, it is very complicated to solve Schrodinger equation. It can be solved by some approximations. So DFT is one of the approximation, and we can solve the many electron system. So DFT does not calculate the conventional wave function like in Schrodinger equation. We calculate the wave function and we go for further probability density calculations. Here in this case, it derives the electron density function and further calculate the ground state energy. So here a functional is simply function of a function. So what is the functional? So here total ground state energy of system is a unique functional of its electron density. So we are considering electron density. We are not considering single electron present in the orbital. We are considering total density of electrons present. So the equation can be written as the ground state energy is function of the electron density. So here is the picture. So for many body perspective, if you consider, so this is ion and these are electrons present. So when you calculate the Schrodinger equation, you cannot neglect the interaction between the adjacent electron, the other electrons, and the ion itself. So there is a very complication in the solution when we solve, and it takes a lot of time to solve this. So here DFT what does? DFT consider all these electron density as a single function and solve the solution and find the solution. This is the main idea of the density functional theory. Now, what are the system requirements for DFT calculation? So if you do a DFT calculation for small structures, like 1 unit cell or 2 unit cell, 2 unit cell is much higher, 1 unit cell is okay. So if you have 1 unit cell and if you are calculating for the electronic properties and some other magnetic properties, some mechanical properties, if you are calculating, a processor with i7 or M2 with approximately 24 GB RAM is enough to do this calculation. And you can find many commercial and free software to do these DFT calculation methods. And if you consider the most famous code is WASP. So it is a commercial software, and there are some free, like Quantum Espresso is a freeware you can use and directly install in your PC and do the DFT calculations. So generally a high-speed computation is necessary for DFT calculation. If you are doing like a big cell or large number of consisting calculation, then you particularly need supercomputer. So then only you can complete your calculation and come to the expected results. So these are the two very famous cores used in the DFT calculation methods. Now, how the DFT calculation works? So how you use materials and how you predict properties. So this is the main important point. So theoretically, we predict the uh, structural properties, mechanical properties, electronic properties, and reaction mechanism, everything we can predict by DFT. So for that, first we need to optimize the material. So let us consider this is the bulk material and this is the surface material. So these two have different applications. So bulk material, if you use bulk material, then you can calculate its mechanical property, you can calculate its electronic property, or you can calculate its structural properties. The surface models are particularly used for the reaction mechanism analysis. So in that process, what you have to do? Let us consider the water splitting mechanism we are discussing. So if you are doing water splitting, first you have to optimize the bulk structure. So let us consider this is bismuth vanadate, which is considered as one of the best photoanode for producing oxygen, the side reaction of HER. So first you have to optimize the atomic positions and other lattice parameters, size and shape of the unit cell. And finally, you get some total energy at the ground state. So once you finally optimize the bulk structure, then you have to cut the slab. So how to cut the slab? So there are different softwares available so that you can cut the slab, or manually you can cut the slab. So what is meant by cutting the slab? So let us suppose you are dealing with bismuth vanadate, and after synthesizing, you do XRD measurements and you find there are different HKL pens available. So if 010 peak or the plane is dominant in that XRD, you can say the 010 surface is dominant, means you have to use that surface for water splitting mechanism. So we cut that surface and we introduce vacuum above the surface to absorb water molecules and the reaction intermediates on the surface. And similarly, you can calculate the For bulk properties, you can calculate elastic constant, hardness and strength, and band structure, density of states, optical properties, etc. Now, particularly for water splitting, what we do. So as I said, first we have to optimize the bulk structure and cut the surface. So there are different possibilities of the surface available. So from XRD, you can come to the conclusion which surface is dominant. So for example, 111, 100, 110. So if you consider nickel, 111 is very dominant. If you consider hematite, 110 is very dominant. So you cut the surface. After that, you have to find out the active sites present. So which active site is more favorable for water adsorption on the surface. And then you go for the reaction mechanism calculation and the key activities. So what are the activities we have to do? So first, we have to cut the surface like this and just put the molecules on the surface. So like this is H2O on the surface, like OH, O, OOH, and finally the O2. This is the step for OER reaction, so oxygen evolution reaction. So first we find out the binding energy. First we put any molecule on the surface of the material and find out the binding energy or adsorption energy of that molecule on the surface. So according to this definition, the more negative adsorption energy indicates the stronger adsorption. But here we cannot say that the stronger adsorption always gives you better performance. Here comes the Sabatier principle. So if we have more strong adsorption energy, the molecules will be always on the surface of the material. So they will not allow other intermediates to come and stick again. So this will possibly poison your electrode material, and eventually what will happen, the performance will decrease. So the binding energy or the adsorption energy should not be high or should not be low. It should be optimal value. So our aim is to find out the optimal adsorption energy where the HER and OER both can happen very easily. Now, after calculating that binding energy, we use other calculations to find out the Gibbs free energy. This is a very important parameter. This is a very important parameter to consider the reaction mechanism in OER and HER. So this Gibbs free energy consists of the E, which is we already calculated the adsorption energy. Then ZPE, the 0 point energy, and T and S. T is the temperature and S is the entropy. So we do other calculations to calculate 0 point energy. So we do frequency calculations to calculate the 0 point energy and entropy change. Once we get all these data, then what we do, we produce a free energy diagram. This diagram shows you the free energy diagram, and this y-axis shows the Gibbs free energy. So in water splitting mechanism, the Gibbs free energy shows you how the potential is there in between the intermediate steps. In the ideal catalyst, the difference between the steps should be 1.23 volt. Then only the water splitting happens at 1.23 volt. Again, we can use this free energy diagram to find out the rate determining step. So what is this rate determining step? The rate determining step identifies the highest energy barrier step. So where is the problem? What step is making an issue to produce oxygen or hydrogen? So we can identify that and predict the over potential. Over potential is like the extra potential needed to produce oxygen or hydrogen beyond 1.23 volt. Now here comes the water splitting. So water splitting is process of using energy to separate water into its constituent elements like hydrogen gas and oxygen gas. And this is the endothermic process, so which eats energy. So these are the two actually reactions happen at the cathode and anode. So HER is a 2-electron reaction and OER is a 4-electron reaction. So 4 electrons are required and 2 electrons reactions. So this is a general 2-electrode system showing electrochemical water splitting, cathode at which H2O converted to hydrogen and water converted to oxygen. So in ideal reaction conditions, the thermodynamic 1.23 volt is needed to drive electrochemical water separation or water splitting. Now let us consider hydrogen evolution first. Now this water splitting can be done by two different methods that we ultimately study more is electrochemical water splitting and photoelectrochemical water splitting. In both the case, the reaction mechanism is same. Only in photoelectrochemical water splitting, you need semiconducting materials, and in electrochemical water splitting, you need metallic materials. So in HER, so hydrogen evolution reaction, it can be done in two electrolytes, two kind of electrolytes. One is acidic electrolyte and one is alkaline electrolyte. So in acidic electrolyte, so we consider there are two reaction mechanisms. One is Volmer-Heroski and other is Volmer-Tuffel reaction pathway. In both these two reaction pathways, there are two steps. Let us consider and discuss one by one. So now consider first the Volmer-Heroski step. Now what is this Volmer-Heroski step? So here are the two steps. So when water is adsorbed, then it is dissociated into in acidic reaction, in acidic electrolytes. So we get one H plus ion, one electron, an active site. The star represents the active sites. And finally, what we get, H is adsorbed on the surface. This step is called as Volmer step. In the next step, the Heroski step, this adsorbed hydrogen interacts with this ion, H plus ion, and this electron to give hydrogen gas, and active site is again free, so that other H plus ion come and attach to the surface. This reaction goes on and we get H2 continuously. What happens in the Volmer-Tuffel pathway? Here, the Volmer step is similar to the previous Volmer-Heroski step pathway. But in the second Tuffel slip, what happens? This H star reacts with another H star, or the H adsorb on the surface, and produces hydrogen gas and produces two active sites. So here the active sites increases, here we have only one active sites. So two different mechanisms. It is very difficult to identify in experimentals which pathway is dominant. Sorry. So by using whole scavenger, you can restrict one reaction pathway and promote other reaction pathway to happen. So, but you have to use a whole scavenger. What happens in alkaline electrolytes? So in the typical process of HER of the alkaline electrolyte, it is only Volmer-Heroski step. And it is also happens in two steps, Volmer step and Heroski step. So first step, as we have already discussed, so here water is adsorbed on the active site and it produces two different species. H is adsorbed and OH is free. In the next Heroski step, this water and adsorbed hydrogen plus one electron gives hydrogen gas plus one OH site, OH ion, and one active site. So in alkaline, in acidic, there are different reaction mechanisms. So what happens in oxygen evolution reaction? So as we have discussed already, the HER is a 2-electron reaction process and oxygen is 4-electron reaction process. So in oxygen evolution reaction, it also takes place in both the electrolytes, acidic electrolyte as well as alkaline electrolytes. So what are the different steps? So water, this is active site, absorption active sites. So when it dissociates, so OH is adsorbed and this H plus is free in the electrolyte with 1 electron. Next step, this OH adsorbed converted into O adsorbed and gives out 1 H plus ion and 1 electron. Then the water molecule interacts with adsorbed oxygen, produces this OH species plus 1 proton plus 1 electron. Final step, this OH adsorbed gives 1 free active site, O2 is evolved, and H plus an electron. So like this, 4 electrons are available and 4 H plus are available. That's why it is called as 4-electron process in acidic electrolytes. What happens in alkaline electrolytes? In alkaline electrolytes, so when we use like alkaline electrolyte means KOH if we use, so we have OH minus species available which adsorb on the surface giving 1 electron. This OH adsorbed with another available OH minus combines together and form O's absorption species and gives us water plus 1 electron. Similarly, these O adsorbed with OH minus species gives OH and plus 1 electron. And further the reaction goes on with 4 electrons available. However, we consider this thermodynamic potential 1.23 volt ideally, but always when we do the experiments, it is not possible at 1.23 volt. There is always an extra potential required to split water into hydrogen and oxygen. So we need some extra potential. That potential is called as over potential on both the electrodes. So our aim is to reduce this over potential, find such materials which can do the splitting of water at particularly 1.23 volt or lesser than that. Now, what is the difference between electrocatalysis and photocatalysis? So electrocatalysis, we use electrical energy as a supply, as an input energy to drive the electrons and other ions. So what kind of catalyst we use? We use conducting catalyst or metals like platinum, iridium, ruthenium oxides. And what is the mechanism? External voltage drives the electron transfer. But in case of photoelectrocatalysis, solar energy, we use renewable energy to drive this splitting of water. Most of the semiconductors are used in photoelectrocatalysis, like TiO2. Hematite is very famous, and they are coated on the FTO and ITO substrates. FTO is fluorine-doped tin oxide, and it is indium-doped tin oxide substrates, which are conducting. Now here what happens, the light absorption generates electron and hole pairs within the semiconductor, which then participate in the redox reactions. So hydrogen production and oxygen evolution reaction with external bias. Now our aim is to synthesize or manufacture better electrocatalyst and photoelectrocatalyst to drive this HER and OER easily and produce hydrogen and oxygen at very low potential. So these electrocatalysts play and the photocatalysts play a crucial role in water splitting by facilitating the charge transfer and lowering the energy barriers of the reactions. So they do reduce the over potential, accelerate the reaction kinetics, and facilitate the charge transfer. Now, the state-of-the-art commercial system, they use platinum, which is very expensive. So that's why we are looking for alternative materials which can drive these reactions at lower potentials. The challenge is high cost and the scarcity of these noble metals. for the commercial production of green hydrogen. Now, what is the electrochemical testing we require? So when we do electrochemical testing or photoelectrochemical testing, we need two kind of systems. One is 3-electrode system, and other is 2-electrode system. This 3-electrode system consists of one reference electrode, one counter electrode, and one working electrode. So working electrode is your active material. So which one you are using for driving the reaction. And this is the counter electrode you are considering as like a best one for both HER and OER. Suppose if you are doing HER, hydrogen evolution, in that case, you can use graphite rod or carbon as a counter electrode. You cannot use platinum here because platinum itself contribute to the HER. In that case, your working electrode cannot be utilized in the correct manner. So your working electron will show higher performance than the original performance since you are using platinum as a counter electrode. So in that case, you have to use some other counter electrode like graphite rod or carbon paper or graphite sheet as a counter electrode. And the reference electrode, you can use different types of reference electrode, like you can use AgAgCl electrode, or you can use mercury oxide electrode or standard calomel electrode as a reference electrode. In case of 2-electrode system, now this is our lab-made 2-electrode system where we can use this for overall water splitting performance to get the overall water splitting performance. So HER and OER can be done together in a single electrolyte, acidic as well as alkaline. So here in this case, we use the alkaline electrolyte, and these are the two electrodes, anode and cathode, made up of same material. So here we show the same material can be used as anode as well as cathode. And further, you can analyze the output of the reaction like hydrogen and oxygen by using the GCMS sample measurements. Basically, you need this electrochemical workstation to do all the tests. So what kind of test do you do? So first we do the linear sweep voltammetry. The linear sweep voltammetry is a curve which can characterize the HER or OER performance. So from that you can calculate the ore potential. How the ore potential is calculated? Let us consider we are dealing with the oxygen evolution reaction. So when we consider the half cell measurements for HER as well as OER. So in case of OER, the ore potential is calculated as the observed potential for a particular current density. Let us suppose consider we are considering a current density of 10 milliampere per meter square or per centimeter square. 10 milliampere per centimeter square if we are considering. So the current density at that particular voltage. So let us suppose we are getting a 10 milliampere per centimeter square current density as 1.3 volt. In that case, the ore potential is 1.3 volt minus 1.223 volt. So almost 0.7 volt is the ore potential. So this is 0.7 volt extra potential is required to drive that reaction, and we are getting oxygen. Similarly, we can calculate the onset potential. Onset potential is the term used to identify where is actually or what potential actually the reaction started happening or the current started increasing. So that potential is called as onset potential. We can calculate the current density as I said. Then we can calculate the Tuffel slope. Tuffel slope is actually the important parameter in HER and OER, which determines the rate of reaction. So how reaction is going on. So what speed? So we can calculate lower the Tuffel slope, higher the reaction activity. And then we can again check the stability by doing the linear sweep voltammetry. So we can check the linear sweep voltammetry after 1,000 cycles, 10,000 cycles, and check the LSV is similar or the current density at a particular voltage is same or not. So we can determine the stability of the material also. Next, we do electrochemical impedance spectroscopy to find out the charge transfer resistance, the solution resistance. So what is the value of resistance? We can calculate by electrochemical impedance spectroscopy. We also do the durability test, the chronoamperometry or chronopotentiometry to check the steady current and voltage over time indicates good durability. So your material should show a good stability for a longer time so that it can produce hydrogen and oxygen steadily. Then finally, we calculate the Faraday efficiency. It should be close to the 100%. So how much energy you are giving, it should be completely utilized to produce hydrogen and oxygen. It can be determined from the Faraday efficiency value. So let's consider some case studies. So first is like stability of doped materials. So this is completely related to the density functional theory calculation, theoretical calculation. So here in this work, what we have done, so particularly our aim was to check the stability of bismuth oxide with the titanium doping, zirconium doping, and titanium zirconium co-doping. So here we have doped these materials together and we wanted to check the material is stable or not. So this graph is for formation energy against the chemical potential or the oxygen environment, say. Now this black line represents the titanium doped, a red line represents the zirconium doped, and the blue line represents the titanium zirconium co-doped system. And if you see the formation energy for the titanium and zirconium co-doped system is more negative, means this doping is very much favorable in bismuth oxide and the material is stable. So experimentally, then you can synthesize this material at low temperatures. So we don't need any extra energy to synthesize this material, or we don't need to anneal this sample at very high temperature to form this titanium and zirconium co-doping. How the formation energy is calculated? So we have this formula to calculate the formation energy. So simple formula we use and calculate the formation energy. So here the ETI dope means we use this titanium doped bismuth oxide and we optimize it by using density functional theory calculation and we get some ground state energy. Now that ground state energy and the total energy we call this ETI doped. Similarly, we calculate it for pure system. And then we calculate the chemical potential of titanium, we calculate the chemical potential of bismuth, and then finally we calculate the formation energy of the system. Now these chemical potentials can be calculated in similar manner for by using titanium bulk system. For titanium metal system, you optimize it, calculate its energy, and do further calculation. You will get the chemical potential of titanium. Similar, you can do for bismuth. So this calculation will finally result into such graphs. One case we did a paper published in this is catalysis back in 2022. So here our aim was to increase the performance of hematite as a photoanode to produce oxygen, a side reaction of HER. So when we measured the performance of silicon doped hematite, the performance was decreased. So we don't know why the performance is decreased. To understand the reason behind it, we did the DFT calculations and we found that when silicon is doped in hematite, it deforms the hematite and we see these ordered regions in silicon doped hematite. So that's why if you see in silicon doping, the formation energy is higher. It is well above the zero. So that's why there is a deformation happen. So then what we did, we used titanium in hematite, and we found the titanium is not making any deformation in the hematite. Then what we did, we incorporated titanium and silicon together to reduce the effect of silicon in the hematite. And surprisingly, we found that the titanium and silicon together, they are like stabilizing the hematite. It will not, they are not deforming the material. And ultimately, when we check the electrochemical performance, the performance was higher. In similar case, we can calculate how the charge is distributed throughout the elements by using density functional theory calculations. Again, let us consider some density of states and band structure prediction by using density functional theory. So in this paper published in Energy and Fields, so this is the case of bismuth and titanium codope system where we calculated the density of states. Now this density of state diagrams will show you how the energy states are occupied in the conduction and valence band. So this is for pure bismuth oxide, where you can see this is 0 electron volt, where the Fermi level is set to 0 electron volt, and this is the conduction band. As we know that the orbitals below Fermi are completely occupied, Fermi level are completely occupied, and orbitals in the conduction band are always empty in case of semiconductors. Now, when we dope the titanium in bismuth oxide, surprisingly, the density of state completely altered. So here the valence band and conduction band positions changed. So titanium doping changed the uh, levels of the conduction band and valence band. And one extra energy state is found near the conduction band. Now here the Fermi level shifts to the conduction band and one extra strap state is found here. Now, since bismuth oxide is a semiconductor, it can be utilized for photoelectrochemical water splitting and other CO2 reduction or other photoelectrochemical applications. Now, this extra trap state is very much important considering the application. So, because when the electron and hole pairs are generated by using solar emission, the electrons emitted from valence band will go here and they will rest here. If they rest here, they can further contribute into the reaction to produce the whatever byproduct we are expecting. But in case of zirconium, there is no trap state observed, so means only the band gap has been reduced a bit. In case of titanium zirconium, so we found there are two trap states can be observed. So these two peaks, which is near to the conduction band, again, it is beneficial for the PC application. Now, this paper published in Journal of Energy Storage, we actually, it is actually related to the energy storage application. But here, actually, we calculated the electronic structure of bismuth sulfide, molybdenum sulfide, and bismuth molybdenum sulfide. And we compared the electronic structure of bismuth sulfide, molybdenum sulfide, and bismuth molybdenum sulfide. So if we look at this carefully, the bismuth molybdenum sulfide has a lower band gap compared to the bismuth sulfide and molybdenum sulfide, which can uh, increase the conductivity of the material and beneficial for charge storage applications. Now, density of states and band structure prediction can be done by using DFT. So we can calculate the ultimate band structure of any material. What is the band gap? Is it a direct band gap or it is an indirect band gap? So we know how we estimate the direct and indirect band gap. So if the conduction band and valence band, they are directly facing each other. Here, in this case, they are not facing each other. So we can say it is an indirect band gap. When they are directly facing each other, then we say it is a direct band gap. So DFT can estimate the nature of band gap also. This case study is regarding the HER production by using a nickel and nickel fluoride nanostructure. So we utilize nickel foam and we uh, check the HER performance of bare nickel foam. So bare nickel foam is considered as one of the substrate for electrode materials used for OER and HER. So here we found the adsorption energies. We did not calculate any gas-free energy and further calculation. On the basis of adsorption energy also, we can little bit determine the performance. So here in this case, we calculated the adsorption energy of water, adsorption energy of OH intermediate, and adsorption energy of hydrogen adsorbed on the nickel atom. So we can see there is a difference in the adsorption energies. So if you see in both the cases for nickel and nickel fluoride, the OH adsorption is very strong. Means here the transition from OH to O adsorption or uh, uh, OH to it is like it is HER. So OH adsorption is higher and this adsorption is lower. In that means H is easily dissolved from the surface instead of OH. So it can produce HR very easily. Now in this paper published in the Nature Communication 2021, so our group find out how hematite shows better performance and how the performance can be increased and what are the uh, what we can say the reaction reaction mechanisms responsible for high performance. So here this is for the pure hematite undoped. We calculated the ore potential by using density functional theory. So here the second order reaction is found to be the rate determining step. And when we dope germanium, so germanium is doped by substituting hematite. So the ore potential is decreased to 0.88 electron volt. So still it is very high ore potential, but the reaction, the rate determining step changes from the second order to third order. Now, this data is very much um, corroborated with the other previously reported papers recently back in 2020. So Professor James Durant, he published one paper in Nature Chemistry suggesting hematite shows the third order reaction to produce oxygen. So this data also matches with that paper published in Nature Chemistry. This is one paper published in ACS Energy later. Some other group, this is not related to our work, but I would like to show how the HER gives free energy is determined. So ideally the gives free energy should be zero. It should be here. So in this case, intentionally I put this data here. So this nickel 111 shows the lowest H adsorption gives free energy. And if we see here, the H adsorption energy is 0.51. Now, when we add the ZPE and entropy term here, ultimately the value will be the same. So when we add the ZPE and TS value, it will be same. So our data is also corroborating with these findings. So recently, early this year, we published one paper in International Journal of Hydrogen Energy considering bismuth oxychloride as a bifunctional electrochemical water splitting electrode. So here, actually, bismuth oxychloride is a semiconductor material. It's not a metal. So here we show that metal oxides also can be utilized as electrocatalyst for HER and OER reactions. So simply, this is very simple method and very cost-effective method. That's why I would like to show this. So it can be produced in minutes. So, and then after we have to just anneal at different temperature. So we studied this and experimentally we found. So this is the LSV curve for different VOC samples A, B, C, D. The samples A, B, C, D means annealed at different temperature. A at 50, B at 150, C at 300, and D at 600. So annealed at different temperature, if you see the sample B, BOCB is showing a higher current and faster reaction kinetics. This red line or black line, blue line or pink line, it should be tilted towards the y-axis, then we can say the reaction kinetics is high. And from this LSV curve, we can calculate the ore potential as I have discussed in the last PPTs. So ore potential, we found lesser for this B sample, almost 286 millivolt. So which is much lesser if we are considering a semiconductor material. So it is very less. And you can ask what is this peak? This peak corresponds to the nickel oxide since we are using nickel foam as a electrocatalyst substrate. So this is from that nickel foam. Then we calculated the tuffle slope and we found that, as I discussed earlier, lower the tuffle slope, higher the performance. So we found that tuffle slope nearly 114 millivolt. And then we discussed, uh, measured the HER performance of this BiOCl sample, and we found BOCB is better for both OER and HER also. That's why we term it as a bifunctional electrocatalyst. So it is showing OER as well as HER. And for HER, the ore potential is 2 to 3 volts. Still, it is very high, but considering a metal oxide, it is a good performance. And the tuffle slope is also 106 millivolt per decimeter. Now, further to check the stability of this BOC or BIOCL sample, we check the stability for 25 hours. So the black one is for OER and red one is for HER. So material was very much stable. Then we did the full cell measurements. Full cell measurements, we used same material as cathode as well as anode, and we found the water splitting achieved at 1.74 volt, means the 10 milliampere per centimeter square current density at 1.74 volt, which results or potential of 0.5 volt at 510 millivolt. Still, it is very high, but considering metal oxide, it's good performance. And again, we check the stability of this assembled device, which is producing oxygen and hydrogen together in a single cell for 20 hours. But overall, the performance is not that good. So then now currently we are working on this BiOCl material and we are modifying the electronic structure and surface of this BiOCl electrocatalyst to increase the performance. This paper is maybe submitted at the end of this year with increased performance. Now, recently, in 2025, last month, we published one paper in Journal Small. So here we did the heterojunction, S scheme heterojunction. You have heard about the Z scheme heterojunction. Now here we introduced, already it is introduced. We have just used this term S scheme heterojunction of hematite with the perovskite material for PEC water splitting application. So when we check the experimental findings of this material, the performance is good. So generally the pure hematite shows the current around 1 milliampere per centimeter square at 1.23 volt. So in case of photoelectrochemical water splitting, we check the current density as 1.23 volt, unlike electrochemical water splitting. In electrochemical water splitting, we consider the current density and the potential. But here, the current density is considered always at the 1.23 volt, and we measure what is the current density. So pure hematite shows only around 1 milliampere per centimeter square at 1.23 volt. So, but when we use this silicon TI doped hematite that we have already published in Nature Communication, so our plan was to again improve the performance of that silicon and TI doped hematite. Okay, what we do, so okay, just modify the surface by introducing one co-catalyst so that the reaction kinetics will be enhanced and it will show better performance. So by using this PBSCF perovskite as a co-catalyst, we increase the performance to 3.70 milliampere centimeter square compared to the previous 2.71 milliampere centimeter square. And why this has happened? Because the charge transfer resistance has been decreased, so lower resistance. And again, the relaxation time decreased only 13%. In the previous case, it was 28.8%. And we calculated the bulk efficiency. It was increased to 40% compared to the previous silicon TiFe203. And again, we calculate the surface efficiency. It is also increased to 78% compared to the previous 64.6%. Again, we calculate the IPC also. So incident photon to current efficiency. So incident photon utilizes most of the energy to produce oxygen and hydrogen. So this PBSCF decorated silicon TiFe203 shows high percentage of IPC compared to the previous silicon Ti hematite. Again, we calculated the donor density. So in case of the silicon PBSCF decorated silicon TiFe203 shows higher donor density compared to the previous silicon Ti doped hematite. So ultimately what we say, so there is a charge transfer happen and somehow the performance is increased. Now we wanted to exactly know how the charge is transferring. Is it transferring from hematite to the PBSCF or from PBSCF to hematite? And at this time, we don't know, is it a S scheme or other Z scheme heterojunction? To estimate that, we did DFT calculation and we found that there is a direct heterojunction contact and there is a Fermi level alignment and band bending and there is the internal electric field at the interface. So we utilize the density functional theory. Here, this is the hematite surface and we put the PBSCF layer on the hematite surface. So there is an interface between these two. And when we did the DFT calculation, we found that this PBSCF gives a charge to hematite and almost 0.17 charge is transferred from PBSCF to silicon Ti hematite. It is setting internal electric field at the interface Since it is setting an internal electric field at the interface and there is alignment, Fermi level alignment and band bending, we say it is a S-scheme heterojunction. So it is published recently in Small. So this DFT calculation demonstrated that electrons are transported from PBSEF to silicon TI in the heterostructure. Now, I would like to discuss this paper published in ACS Energy Letters. This is also a fascinating work we did last year. So here our aim was to enhance the performance of hematite. So for that purpose, we tried different things, how the performance of hematite can be enhanced. So here in this case, we modified the morphology of hematite photoanode. So how actually the hematite is synthesized? So we use hydrothermal method to synthesize hematite on the fluorine doped tin oxide. And then we use germanium dioxide overlayer on the surface of this Ti doped hematite. And what actually happened, it has changed the morphology of hematite. It forms the porous structure. So before doing the experimental, we check the possibility of the stability of material. Is it stable? And how the OER kinetics will run. So for that purpose, we did DFT calculation. So we checked the formation energies and we found that germanium with the Ti and tin is very much stable compared to this other samples. So we have checked different samples with tin doped in hematite, germanium and tin together, and Ti tin together. We found that this germanium, Ti and tin together in hematite showing the best stability, and we found that the germanium tin together showing bad interaction. So they are forming the deformation or distortion in the hematite. That's why the performance was low. So then we introduced Ti and there is no deformation in the unit cell and the structure is well maintained. Then we calculated the OER reaction mechanism on the surface and we found that the Ti tin shows a second order reaction as a rate determining step with ore potential of 1.1 electron volt, which is higher. But in case of the germanium titanium tin doped hematite, it is again the third order reaction mechanism, which is again well matching with the previously reported nature chemistry group. So that nature chemistry group, why I'm just talking much about that, because the study is much more realistic experimental study based on the spectroscopy measurement, how the reaction intermediates are playing in that reaction. So again, it matches with that data with a much lower ore potential of 0.74 electron volt compared to the last Nature Communication paper 0.88 electron volt. And the performance was like 3.4 milliampere per centimeter square at 1.23 volt. And again, we calculated the surface area and current density per surface area. So in this case of germanium Ti tin, it shows higher in both the cases. Here it is 0.7, 0.17. Now what happened to the morphology? So when this germanium Ti tin we used, then we transformed it to the like more porous so that the water intermediates can be easily adsorbed on the surface. So this is actually we think about what actually material is maybe looking like in the microscopic level. Now to realize that eventually we did the HRTM and we found the porous structure, more pores, a little bit smaller particles. So, and it has been confirmed the morphology is altered. So that's why the material shows better performance, and it is published last year in ICIS Energy Letters. So further, we again calculated other parameters to confirm the performance, and we found that after introduction of some like co-catalyst, the performance again increased to 4.5 milliampere per centimeter square. So again, we increased compared to the last. So more theoretical current density is around 12 milliampere per centimeter square, but we reached around 4.5 milliampere per centimeter square. So recently, we are again trying to increase this current density by further modification in hematite. Again, we calculated this bulk efficiency. We calculated the surface efficiency, the charge transfer. The charge transfer in case of this highly porous germanium-tin hematite is much reduced compared to the other samples. And then again, we calculated IPC, the stability, which is much more stable for 100 hours we calculated. And we compare the performance with other reported papers. So this work shows high performance current density compared to other papers. So thank you so much. I really thank our Minister of Technology for giving me this opportunity. Again, I thank you, Dr. J.D. Patil, sir, coordinator of this Atal FDP program, Dr. Lakshman Jetta, sir, co-coordinator of this program, and my friend Vital Hirade. Thank you so much.
Thank you, sir.